Consciousness is the one thing we experience more directly than anything else, yet we have no clear understanding of what it is or how it arises. It is the state of being aware, of having thoughts, feelings, and perceptions. We take it for granted, but when we try to explain how it emerges from the physical brain, the answers become elusive. Imagine waking up in the morning. You open your eyes, feel the warmth of the blanket, hear the sounds of birds outside. You recognize the room around you, remember where you are, and recall who you are. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries. These experiences seem effortless, but the process behind them is deeply complex. Your brain, a biological structure made up of neurons, somehow generates a first-person experience of the world. But the question is how? The brain operates through electrical and chemical signals. Neurons send messages to each other, forming intricate networks. Scientists can track these signals, observe which areas of the brain light up when you see an image or hear a sound, and even predict what you are about to say or do in some cases. But nowhere in these processes do we find an explanation for why we experience the world the way we do. This gap between physical processes and subjective experience is what makes consciousness such a mystery. Let's take an example of a computer. It processes information, takes input, and produces output. It can recognize faces, respond to commands, and even simulate conversations. Yet no matter how advanced, it does not feel anything. A camera linked to an AI program can detect colors, but it does not experience red the way you do. But it does not have an inner life. The question is why the brain, which also processes information, has an internal world while a computer does not. One of the most puzzling aspects of consciousness is its unity. You hear, see, touch, and think, but all of these inputs blend into a single experience. The brain processes vision in one region, sound in another, and touch in yet another. But you do not perceive these as separate. When you watch a movie, the dialogue, the images, and the music come together as a seamless experience. How does the brain bind all of this information into a unified moment? Another challenge is the way consciousness seems tied to attention. When you focus on something, it enters your awareness, but when you ignore it, it seems to disappear. Consider driving a familiar route while lost in thought. You reach your destination without remembering the details of the drive. Your brain processed the road, controlled the car, and responded to signals, but your conscious mind was elsewhere. Why is some information available to awareness while other processes run in the background? Some scientists argue that consciousness is just an illusion, a byproduct of brain activity with no deeper significance. They suggest that the brain creates a model of reality and that our sense of self is just part of that model. Others believe that consciousness serves a crucial function, allowing complex decision-making and social interaction. If it were just a byproduct, why would evolution have favored it so strongly? There are many theories about how consciousness arises. Some propose that it emerges from the complexity of neural connections. The more interconnected a system is, the more conscious it becomes. This idea suggests that consciousness is not unique to humans, but exists in varying degrees in animals and even artificial systems. Others argue that consciousness depends on specific patterns of brain activity rather than just complexity. One radical theory suggests that consciousness is a fundamental property of the universe, like space and time. This idea, known as panpsychism, suggests that even simple particles have some level of experience, and that the brain does not create consciousness but instead organizes it in a way that allows for complex awareness. While this idea is speculative, it highlights the difficulty of explaining consciousness purely in terms of physical processes. Brain injuries and disorders offer some clues about consciousness. Patients with damage to certain areas of the brain lose specific aspects of awareness. Some lose the ability to recognize faces, even though they can still describe facial features. Others lose awareness of one side of their body while still being able to move it. These cases show that consciousness is not a single thing, but a collection of abilities supported by different brain regions. One of the most mysterious conditions is locked-in syndrome, where a person is fully conscious but unable to move or communicate. This condition reveals that awareness can exist even when almost all outward signs of it are gone. But on the other hand, some patients in comas or vegetative states may show brain activity similar to wakefulness, but with no sign of experience. Understanding these states may help uncover the mechanisms that create conscious awareness. Sleep and anesthesia also offer insights. Every night, you lose consciousness, only to regain it in the morning. What changes in the brain to switch awareness off and on? Under anesthesia, patients can undergo major surgery without experiencing pain or memory of the event. This suggests that specific brain functions are necessary for consciousness and that disrupting them can make experience disappear completely. But why does turning off certain brain activity erase the feeling of being alive? Artificial intelligence raises further questions. If a machine became advanced enough to mimic human behavior perfectly, would it be conscious? Could a computer ever truly experience pain, joy, or curiosity? If not, what is missing? Understanding consciousness may help us answer these questions and determine whether awareness requires a biological brain or if it could emerge in other systems. For now, consciousness remains one of the biggest mysteries in science and philosophy. We know it exists because we experience it firsthand, but we do not know how it works or why it exists at all. Until we understand the link between the physical brain and subjective experience, the nature of consciousness will remain one of the greatest puzzles of reality. Time shapes everything we do. We wake up, go to work, grow older, and remember the past. Clocks tick forward, never backward. But what is time really? Is it something real or just an illusion we experience? Scientists and philosophers have wrestled with this question for centuries, and despite all our advances, we still don't have a definite answer. We experience time as a flow. One moment replaces another, and we can't stop it. We were children once, then adults, and eventually, we grow old. This gives us the sense that time moves forward, but physics tells a different story. In the equations that describe the universe, time doesn't have a direction. The laws of physics work the same way forward and backward. If you watched a video of planets orbiting the sun, you wouldn't be able to tell if it was playing forward or in reverse. The same goes for most physical processes at a fundamental level. This suggests that time might not flow the way we feel it does. A strange thing happens when you look at time from Einstein's perspective. His theory of relativity tells us that time is not separate from space. Instead, they form a single structure called spacetime. In this framework, time does not move. It simply exists like the three dimensions of space. A tree has height, width, and depth, but those don't change as you walk around it. If time is just another dimension, then the past, present, and future all exist together. This is sometimes called the block universe theory, where all moments exist at once, like pages in a book. You might experience only one page at a time, but all the pages are still there. This idea conflicts with how we feel about time. We can move freely in space, but we can't jump to next week or last year. If the past and future already exist, why can't we see them? One answer might be our brain's way of processing information. We form memories, which let us recall the past, but not the future. This could create the illusion of time moving forward. Our sense of now may be nothing more than a mental construct, a way for our brains to organize events. Another way to think about time is through entropy, which measures disorder. A clean room gets messy over time, but it doesn't clean itself. A broken egg won't put itself back together. This is because there are more ways for things to be disordered than ordered, and natural processes tend to move toward disorder. This principle, called the second law of thermodynamics, gives time its arrow. It explains why we remember the past and not the future. A shattered glass has more ways to be broken than to be whole, so we only see it happen in one direction. But this still doesn't prove time is a real thing. It only shows that the universe has a tendency to behave a certain way. Time also behaves strangely when you move fast. According to relativity, the faster you go, the slower time moves for you. A person traveling close to the speed of light would experience time much slower than someone on Earth. This has been tested with atomic clocks on fast-moving jets, which return slightly behind their stationary counterparts. The effect is small at everyday speeds, but becomes extreme as you approach the speed of light. If a person left Earth and traveled at near light speed for what felt like a few years, they might return to find centuries had passed. This shows that time is not absolute. It changes based on motion and gravity. Black holes reveal even more about time's mysterious nature. Near a black hole, gravity is so strong that it stretches time. If you watched someone fall into a black hole, you would see their movements slow down until they seemed frozen. But for the person falling in, time would feel normal. If they looked outward, they might see the entire future of the universe unfold in an instant. This suggests that time is not something we all experience in the same way. If time is not a steady flow, and if all moments may exist together, then could our experience of time be just a limitation of how we perceive reality? Some physicists suggest that what we call time is just a way of organizing change. Without change, there would be no way to tell one moment from another. If all the clocks in the world stopped, if no one moved, if nothing changed at all, would time still exist? Or is it simply a relationship between events? Quantum mechanics adds another layer of mystery. At the smallest level, particles don't behave in ways that fit neatly into our sense of time. They can exist in multiple places at once, and they only settle into a definite state when observed. Some interpretations suggest that time might emerge from a deeper, timeless reality. If that's the case, then time might not be a fundamental part of the universe at all. It might be something we experience only because we live on a human scale. If time is an illusion, does that mean free will is an illusion too? If the future already exists, then are we just playing out events that are already set? Some scientists argue that the block universe means everything is predetermined. Others believe that quantum mechanics, with its element of randomness, could leave room for free will. The truth is, we don't know. Our daily experience tells us that time is real. We age. We make choices. We move from one moment to the next. But the deeper we look, the less certain time becomes. It might be a dimension we only perceive in a limited way. It might be an emergent property of the universe. It might not exist at all. For now, time remains one of the biggest mysteries in physics and philosophy. Whether it flows, stands still, or is just an illusion, we are bound by it. We wake, we sleep, we live, and we wonder. The Big Bang is the starting point of the universe as we know it. Scientists say it happened about 13.8 billion years ago. Everything, including space and time, came from a single, incredibly dense and hot point. But this explanation leaves out a big question: what came before it? For a long time, many scientists said that question didn't make sense. If time began with the Big Bang, there was no before. Asking what happened before time existed would be like asking what's north of the North Pole. But this answer doesn't satisfy everyone. It also doesn't rule out the idea that something led to the Big Bang, even if it wasn't before in the way we usually think about time. Some scientists think that another universe may have existed before ours. One idea is called the cyclic universe theory. It suggests that the universe expands, then collapses back into a dense state, and then explodes into another Big Bang. This would mean the universe has gone through endless cycles of birth and rebirth. Each cycle could erase the past, making it impossible to know what came before. But the idea still allows for a before in some sense, even if it's not the same kind of time we experience now. Another theory suggests that our universe formed from the collision of higher dimensional spaces. In string theory, the universe might be a giant membrane, or brain, floating in a higher dimensional space. If two of these brains collided, the energy from the impact could have created what we see as the Big Bang. This would mean our universe isn't the first, and it isn't alone. Instead, it's part of a much larger reality, with other universes forming and collapsing all the time. Quantum mechanics adds another layer to the mystery. At very small scales, reality doesn't follow the rules we see in everyday life. Some physicists think the universe came from a quantum fluctuation. In this view, space is never truly empty. Instead, tiny particles and fields appear and disappear all the time due to quantum mechanics. If a random fluctuation had enough energy, It might have triggered the rapid expansion that became the Big Bang. This suggests that something existed before our universe, even if it was just a strange, ever-changing quantum field. Another idea is the multiverse. Some theories suggest that our universe is just one of many. New universes might be forming all the time, and the Big Bang was just the birth of one particular universe among many. If this is true, then something did exist before the Big Bang, other universes. But we might never know anything about them, because the expansion of our own universe has cut us off from any direct evidence. Some scientists think that time itself might be an illusion. Instead of a past, present, and future, time could be just a way humans make sense of change. If time is a feature of the universe rather than something independent, then the question of what happened before the Big Bang might not have an answer. Instead, what we see as time may have emerged along with space and matter in the Big Bang itself. Observations of the cosmic microwave background, radiation left over from the Big Bang, have given scientists clues about the early universe. Some researchers look for patterns that might hint at an earlier state, but so far, nothing definitive has been found. Future discoveries might help us understand whether something existed before the Big Bang, or if the question itself is based on assumptions that don't apply to the universe. The challenge with all these ideas is that they are hard to test. The Big Bang erased almost all evidence of what came before it. The farther back we look, the harder it becomes to get clear answers. But science is always advancing. New observations, better models, and deeper understanding of physics might one day give us a clearer picture of what, if anything, came before the Big Bang. For now, the question remains open. Theories exist, but none are proven. Some scientists think we will never know, while others believe future discoveries could reveal surprising answers. Either way, the mystery of what came before the Big Bang continues to challenge our understanding of reality. Everything we see, hear, and experience exists. The stars, planets, oceans, and even the thoughts in our heads are part of reality. But why is there anything at all? Why is there something instead of nothing? This question has puzzled philosophers, scientists, and theologians for centuries. If we think about nothing, we imagine an empty void. But even a void is something. It has space. A true nothingness would have no space, no time, no laws, no potential for anything. That kind of nothing is hard to grasp. So why do we have a universe full of matter, energy, and order? Some people turn to religion for an answer. Many traditions say a higher power created the universe. But that leads to another question. Why does that higher power exist? If God or a creator is the explanation, then we are left with the mystery of why God exists instead of nothing. The question does not disappear. It shifts to a different level. Science approaches the question differently. The Big Bang Theory tells us the universe had a beginning. About 13.8 billion years ago, everything we see today emerged from a single dense point. Space and time began. But why did it happen? What came before it? Scientists don't have a definite answer, but they have ideas. One possibility is that the universe came from a quantum fluctuation. Quantum mechanics, the science of very small things, shows that particles can appear and disappear from empty space. If a small amount of something can come from nothing, maybe the whole universe did too. But if this is true, we still need to ask why quantum laws exist at all. Why do these rules allow something to appear instead of leaving nothing alone? Some scientists suggest our universe is part of a multiverse. Maybe there are countless other universes, each with its own properties. If universes are always forming, then the question of why this one exists becomes less puzzling. It is just one among many. But even if the multiverse exists, we still have to ask why the multiverse itself exists. Another idea is that the universe exists because it must. Some thinkers believe that certain mathematical truths cannot be avoided. 2 + 2 = 4, no matter what. It is not a choice or a random event, it simply is. Maybe the universe follows similar necessary rules. But if this is the case, why do those rules exist? Philosophers have another angle. Some argue that nothingness is unstable or impossible. Maybe true nothing cannot exist, so something must exist instead. But why? And if nothingness is unstable, what makes it so? Another perspective is that we are asking the wrong question. Maybe existence is the default, and it is nothingness that needs explaining. We assume that nothing should be natural and something should be unusual. But what if it is the other way around? Our minds struggle with these ideas because we are used to cause and effect. We assume everything needs a reason or a cause. But if the universe is all there is, then what could cause it? Asking why the universe exists might be like asking what is north of the North Pole. The question assumes something that may not apply. Some people say this question is unanswerable. Maybe our minds are not built to understand the reason for existence. Just as a dog cannot grasp algebra, we might not be able to grasp the nature of existence. But giving up on the question does not make it go away. Others argue that the question itself is proof that the universe must exist. If there were truly nothing, then no one would be here to ask why. The fact that we can even ask the question means there is something rather than nothing. But this does not tell us why it is that way. Science keeps searching for answers. New discoveries in physics could shed light on why the universe is here. Maybe a future theory of everything will reveal the underlying cause of existence. But even if we find an answer, we may still wonder why that answer is true. The mystery of why the universe exists touches everything. It is the deepest question of all. It makes us reflect on our place in the cosmos. Whether we turn to science, philosophy, or faith, the question remains. It is a reminder that some mysteries go beyond our current understanding. But even without a clear answer, the question itself shapes how we see the world. The universe is changing. It has been changing since the moment it began, and it will continue to change long after everything familiar is gone. Stars burn through their fuel, galaxies drift apart, and space itself stretches. The question is, where does all of this lead? Will the universe keep expanding forever? Will it slow down and collapse? Or will something more dramatic happen, tearing everything apart at a fundamental level? To understand where the universe is going, it helps to look at where it has been. Everything began with the Big Bang. Around 13.8 billion years ago, the universe was packed into a space so small and dense that physics as we know it no longer applied. Then, for reasons not yet fully understood, it expanded. This wasn't an explosion in the traditional sense. There was no center, no empty space outside for it to expand into. Space itself stretched. Galaxies didn't shoot outward through pre-existing space. Instead, the fabric of space grew, carrying them with it. For a long time, astronomers assumed this expansion must be slowing down. The logic was simple. Everything has gravity, and gravity pulls things together. The galaxies in the universe attract each other, so their motion should be slowing as they resist the pull of gravity. The question was whether gravity was strong enough to eventually reverse the process. If the universe had enough mass, then at some point gravity would stop the expansion and pull everything back. This scenario is known as the Big Crunch. Over billions of years, galaxies would move closer, temperatures would rise, and everything would collapse into a hot, dense point, similar to how the universe began. Some theorists even suggested this could lead to a cycle where the universe expands, collapses, and then starts over with another Big Bang. But something unexpected changed this idea. In the late 1990s, astronomers studying distant supernovae discovered that the universe wasn't just expanding, it was expanding faster over time. This meant some force stronger than gravity was pushing things apart. Scientists called this force dark energy, though they still don't know exactly what it is. With dark energy driving expansion, the Big Crunch now seems unlikely. Instead, the universe appears to be headed toward one of two possibilities. In one scenario, expansion continues at a steady rate. Galaxies will drift farther apart, and over trillions of years, the universe will grow cold and empty. This is often called the Big Freeze or heat death. In this future, stars will burn out one by one. Without new stars forming, the universe will become dark. The last remaining energy will spread so thin that nothing interesting will happen anymore. It will be a vast, empty place with no heat and no motion. The other scenario is more extreme. If dark energy grows stronger over time, the expansion will speed up more and more. This could lead to a big rip. Instead of galaxies just moving apart, the force pushing them outward would become so strong that it would overcome gravity, electromagnetic forces, and even atomic bonds. First, galaxies would separate. Then solar systems would be torn apart. Eventually, even atoms would break down. Space itself would be torn to pieces, ending the universe not with a slow fade, but with everything being destroyed. Which future is correct? Scientists are still trying to figure that out. They study dark energy by observing distant galaxies, trying to measure how expansion has changed over time. The problem is, dark energy is unlike anything else we've encountered. It doesn't behave like matter or normal energy. It doesn't clump together. It seems to remain constant or possibly even grow stronger. Because we don't fully understand it, we can't be sure what it will do in the distant future. There's also another unknown factor: the possibility that something unexpected will happen. Just as dark energy was a surprise, there could be other forces at work that we haven't discovered yet. Some theories suggest that dark energy could eventually fade, allowing gravity to take over. Others propose that the universe could transition into a new state, causing space itself to behave differently. One idea even suggests that a vacuum decay event could end everything instantly. If a lower energy state of the universe exists, a random quantum event could cause a bubble of this new reality to form. This bubble would expand at the speed of light, erasing everything in its path. If this is possible, it could happen at any time, with no warning. For now, the universe is changing. It has been changing since the moment it began, and it will continue to change long after everything familiar is gone. Stars burn through their fuel, galaxies drift apart, and space itself stretches. The question is, where does all of this lead? Will the universe keep expanding forever? Will it slow down and collapse? Or will something more dramatic happen, tearing everything apart at a fundamental level? To understand where the universe is going, it helps to look at where it has been. Everything began with the Big Bang. Around 13.8 billion years ago, the universe was packed into a space so small and dense that physics as we know it no longer applied. Then, for reasons not yet fully understood, it expanded. This wasn't an explosion in the traditional sense. There was no center, no empty space outside for it to expand into. Dark matter is one of the biggest mysteries in science. It makes up most of the mass in the universe, yet no one has ever seen it. Scientists can't touch it, and it doesn't emit light. It doesn't reflect or absorb anything on the electromagnetic spectrum. It doesn't behave like the matter we see around us, yet its effects shape the universe. Galaxies spin faster than they should, and clusters of stars stay bound together in ways that don't make sense based on the matter we can see. Something is holding them together, and that something is what scientists call dark matter. Astronomers first noticed something strange about galaxies in the 1930s. A scientist named Fritz Zwicky studied a cluster of galaxies and realized they were moving too fast. Based on the visible matter, the galaxies should have flown apart. There wasn't enough gravity to hold them together, yet they remained bound. He proposed that an unseen form of matter was providing the extra gravity. At the time, few took the idea seriously, but decades later, scientists found more evidence. In the 1970s, Vera Rubin studied how galaxies rotated. If gravity worked as expected, stars near the center of a galaxy should move faster than stars on the outer edges. This is the same way planets orbit the sun. Mercury, which is close, moves fast, while Neptune, far away, moves slow. But when Rubin measured the speeds of stars in galaxies, she found something unexpected. The stars on the edges of galaxies moved just as fast as the ones near the center. That should have been impossible unless some unseen mass was present. Something invisible had to be contributing to gravity, keeping the stars in place. Scientists ruled out normal matter as an explanation. Dust, gas, or unseen planets could not account for the missing mass. The amount of unseen material needed was far too great. It had to be something else, something that didn't behave like regular matter. Over time, the evidence built up. Observations of galaxy clusters, gravitational lensing, and patterns in the cosmic microwave background all pointed to the same thing. There was a lot more mass in the universe than what could be seen. Gravitational lensing provides one of the clearest proofs. Light bends when it passes through a gravitational field. Einstein predicted this in his theory of general relativity. Scientists can measure how much light bends around a galaxy or cluster of galaxies. When they do, they find that the amount of bending suggests far more mass is present than what is visible. The light from distant stars curves around something invisible. That invisible something must have mass, meaning it has gravity. This effect has been seen countless times, always pointing to the presence of dark matter. The cosmic microwave background, the afterglow of the Big Bang, also contains clues. This faint radiation is spread across the universe, and tiny variations in it reveal how matter was distributed early on. When scientists analyze these variations, they find that ordinary matter alone could not have created the patterns we see today. There must have been more mass shaping the early universe, influencing how galaxies formed. Dark matter is the best explanation. Despite all this evidence, no one knows what dark matter actually is. Scientists have ideas, but none have been proven. One possibility is that dark matter consists of a new type of particle, different from anything in the standard model of physics. Some theories suggest weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass and exert gravity, but would rarely interact with regular matter. Another idea is axions, extremely light particles that could behave in just the right way to explain dark matter's effects. Experiments have searched for these particles, but so far, nothing has been found. Scientists built massive underground detectors filled with supercooled liquid, hoping to catch a rare interaction between dark matter and regular atoms. Other experiments smash particles together at high speeds to see if dark matter emerges. Despite decades of searching, no direct evidence has been found. Some researchers wonder if dark matter is not a particle at all, but rather a sign that we don't fully understand gravity. Maybe our equations need adjusting, and what we call dark matter is actually the result of a deeper law of physics we have yet to discover. Modified gravity theories attempt to explain galaxy rotation and lensing without needing extra mass. These ideas remain controversial because dark matter explains so many things so well, while modified gravity struggles in some cases. The search continues because dark matter is essential to how the universe works. Without it, galaxies wouldn't have formed the way they did. The structure of the universe would be completely different. Every major cosmological model includes dark matter because the evidence demands it. Something unseen is out there, and it shapes the universe on the largest scales. Some ideas suggest that dark matter might interact with itself. It could form its own structures, possibly even dark matter galaxies. If that's true, then the universe contains not just the stars and planets we see, but also an entire invisible framework of dark matter. Some theories even suggest dark matter might weakly interact with normal matter in ways we haven't yet detected. New telescopes and experiments may finally bring answers. The James Webb Space Telescope, particle accelerators, and dark matter detectors continue to probe the unknown. Each new observation refines our understanding, even when results come up empty. Sometimes the lack of a result is just as important because it helps narrow the possibilities. One day, we might finally detect dark matter directly. If we do, it would revolutionize physics. It could reveal a whole new side of reality, showing us particles and forces that were hidden all along. Until then, the mystery remains. We know dark matter exists because of its effects, but we don't know what it is. The universe holds its secrets well, but science keeps pushing forward, searching for answers. Dark energy is one of the biggest mysteries in physics. Scientists know it exists because the universe is expanding at an increasing rate, but they do not know what it is. The discovery of dark energy changed how we think about the cosmos. Before it, most scientists believed that gravity would eventually slow the expansion of the universe. Some even thought it might reverse, causing the universe to collapse. Instead, in the late 1990s, astronomers found that the expansion was speeding up. Something was pushing galaxies apart, and they called this unknown force dark energy. To understand dark energy, it helps to go back to the idea of the expanding universe. In the early 20th century, astronomers thought the universe was static. Then Edwin Hubble found that distant galaxies were moving away from us. This led to the idea that space itself was stretching, which supported the Big Bang theory. But if space was expanding, what controlled the rate? Gravity should have pulled things together, slowing the expansion. That made sense, but then something strange happened. Observations of distant supernovae showed that galaxies were moving away faster over time. Instead of slowing down, the universe was accelerating. At first, scientists were skeptical. The discovery came from studying type Ia supernovae, which act like cosmic yardsticks. Because these supernovae explode with the same brightness, astronomers can use them to measure distances. When teams of researchers compared the brightness of these explosions to how fast their galaxies were moving, they saw something unexpected. The galaxies were farther away than they should have been. This meant the universe was expanding faster now than in the past. This led to a puzzle. What was causing this acceleration? The answer could not be normal matter. Everything we see, stars, planets, even black holes, makes up only a small part of the universe. Scientists estimate that dark energy accounts for nearly 70% of everything. But what is it? One possibility is that dark energy is built into space itself. Albert Einstein once proposed something similar. In his equations for general relativity, he included a term called the cosmological constant. This idea suggested that empty space could have energy. Einstein later removed it, calling it a mistake. But if space has energy, then as space expands, there is more of it, meaning its effect does not dilute. This fits what astronomers see. Another idea comes from quantum mechanics, which suggests that even empty space is not truly empty. Tiny particles pop in and out of existence, creating what physicists call vacuum energy. If this energy pushes space apart, it could explain dark energy. But when scientists try to calculate how much energy this would create, the answer is far larger than what we observe. The numbers do not match, making this explanation incomplete. Some physicists think dark energy might not be constant, but instead change over time. This idea is called quintessence. Unlike the cosmological constant, which stays the same, quintessence would evolve. It could be a new type of field that changes strength as the universe grows. If true, it could mean the fate of the universe is uncertain. It might keep expanding forever, slow down, or even tear apart in a big rip. There is also a chance that our understanding of gravity is incomplete. Einstein's theory of general relativity explains gravity well on large scales, but if it breaks down in certain conditions, we might need a new theory. Some alternative models suggest that gravity behaves differently at cosmic distances, making it look like an unknown force is at work when it is really a property of space itself. Scientists continue to test these ideas. They use telescopes to map galaxies and study how the universe has changed over time. Missions like the Euclid Telescope and the Vera C. Rubin Observatory will collect data to help refine models of dark energy. They will look at how galaxies cluster and how light bends as it travels through space, which can reveal how dark energy affects the cosmos. The mystery of dark energy is fundamental to understanding our universe. If it remains constant, the universe will expand forever, growing colder and more empty. If it changes, the future could be very different. Scientists are still searching for answers, and each new discovery brings them closer to solving one of the greatest questions in physics. Gravity shapes everything we see in the universe. It keeps planets in orbit around stars, holds galaxies together, and makes apples fall from trees. But what is it, really? Most people think of gravity as a force, like a magnet pulling objects together. That idea comes from Isaac Newton, who described gravity as an invisible force that acts at a distance. His equations let us predict how objects move under gravity's influence, and they work extremely well. For centuries, scientists relied on Newton's view because it explained the world in a way that matched observations. Then, Albert Einstein changed everything. He showed that gravity isn't a force at all, at least not in the way Newton thought. Instead, Einstein described gravity as the warping of space and time. According to his theory of general relativity, massive objects bend the fabric of space around them. Imagine placing a heavy ball on a rubber sheet. The sheet bends under the weight of the ball, and if you roll a smaller ball nearby, it moves toward the heavier ball because of that curvature. That's how Einstein saw gravity. Objects follow the curves of space, and what we experience as gravity is actually just the natural movement of things through curved space. This explanation works beautifully for large objects like planets, stars, and galaxies. It even predicts strange effects, like time moving slower in strong gravitational fields. We've tested Einstein's ideas many times, and they've passed every test so far. GPS satellites, for example, must account for time running slightly faster in orbit than on Earth's surface because of general relativity. If they didn't, your phone's navigation would be wildly off. But there's a problem. When we look at the very small particles, atoms, and the quantum world, Einstein's theory doesn't fit. Scientists have spent decades trying to reconcile gravity with quantum mechanics, the framework that describes the behavior of particles at tiny scales. Unlike gravity, quantum mechanics is based on probabilities, uncertainty, and forces that come in discrete packets. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, have quantum descriptions. Gravity does not. This is where the question arises. Is gravity truly a fundamental force like the others, or is it something that emerges from deeper principles? Some physicists believe gravity isn't fundamental at all, but is instead a byproduct of other interactions. They compare it to temperature. Temperature isn't a fundamental property of individual particles. It's a statistical effect that emerges when many particles move together. If gravity works the same way, then what we call gravity might be a large-scale effect of something else happening at a deeper level. One approach to this idea comes from quantum information theory. Some scientists suggest that gravity could emerge from the way information is stored and processed in the universe. The connections between particles and fields might create the effect we call gravity, much like the way collective behavior of water molecules creates the property we call fluidity. In this view, space itself could be made of tiny, fundamental units of information. When those units arrange themselves in a certain way, gravity appears as a natural consequence. Another idea comes from string theory, which suggests that all particles and forces, including gravity, arise from tiny vibrating strings. If true, gravity would not be fundamental, but would emerge from deeper, multidimensional structures. Some versions of string theory predict the existence of extra dimensions beyond the three we experience, and these hidden dimensions could shape how gravity behaves. A different line of thought suggests that gravity isn't even a force, but a consequence of entropy, the natural tendency of systems to move from order to disorder. This approach, known as entropic gravity, argues that space and time themselves emerge from deeper principles related to information and thermodynamics. In this view, gravity is what happens when systems try to balance out energy and information in the most efficient way possible. The challenge is that these ideas remain theoretical. We don't have experiments yet that can confirm whether gravity is fundamental or emergent. General relativity works so well in describing the large-scale universe that it's difficult to test alternative ideas in a meaningful way. Meanwhile, quantum mechanics continues to be one of the most successful scientific theories ever developed, yet it refuses to cooperate with our understanding of gravity. Black holes provide one of the best testing grounds for these ideas. Inside a black hole, gravity is so strong that Einstein's equations break down. At the center, there's a singularity, a point where density becomes infinite and space and time stop making sense. If we understood what happens there, we might unlock the deeper nature of gravity. Some theories suggest that black holes store information in ways that hint at gravity being an emergent phenomenon rather than a fundamental force. Another clue could come from the early universe. Right after the Big Bang, the entire universe was a tiny, dense point where quantum mechanics and gravity must have been intertwined. If we can develop a theory that explains that moment, we might finally understand whether gravity is a force like electromagnetism or a secondary effect of something deeper. For now, we don't know. Scientists continue searching, developing experiments, and refining theories. What we do know is that gravity is central to our existence. It shapes the universe, governs the motion of galaxies, and keeps our feet on the ground. Whether it is fundamental or emergent, it remains one of the biggest mysteries in physics. Physical constants shape the universe as we know it. They include numbers like the speed of light, the charge of an electron, and the gravitational constant. Scientists rely on these values to explain everything from the behavior of atoms to the motion of galaxies. The question is whether these constants are truly constant or if they change over time. Imagine waking up one day to find that gravity feels weaker. If you jumped, you might stay in the air longer than usual. Maybe water boils at a different temperature. If the constants that define the universe were shifting even slightly, the consequences would be massive. The way stars burn, how atoms bond, and the structure of space itself could all change. For now, the physical constants appear fixed. Every experiment, every measurement, and every observation points to the same values across time and space. But this assumption is something scientists continue to test. If these constants ever change, it could mean that our understanding of reality is incomplete. Physicists use telescopes to look billions of years into the past. The light from distant galaxies takes time to reach us. If fundamental constants had shifted, the way atoms emit or absorb light would be different from what we see today. So far, the evidence suggests that these numbers have remained steady. But the universe is vast, and there may be places where things work differently. There are theories suggesting that physical constants might evolve. One idea comes from string theory, which suggests that extra dimensions exist beyond the three we see. If these dimensions shift in size, the constants we measure could change as a result. Another possibility comes from the idea that our universe is one of many. Different universes could have different values for these constants, and we might just happen to live in one where they remain stable. The fine structure constant, which controls how strongly light interacts with atoms, is one of the most studied cases. Some studies have suggested that this number varies slightly when looking at distant galaxies. If true, it could mean that different parts of the universe experience different physics. But these findings are still debated, and many scientists argue that measurement errors could explain the variations. If constants were to shift, even a tiny amount, the consequences would be enormous. The delicate balance that allows stars to shine could break down. A slight change in the strength of the electromagnetic force could mean that atoms no longer hold together the way they do now. Chemistry, biology, and even the fundamental laws that allow life to exist could all be different. We assume constants are fixed because our experience tells us they are. Clocks tick predictably. The structure of matter doesn't suddenly change. When scientists send spacecraft across the solar system, their calculations work perfectly. But our perspective is limited. The universe is billions of years old and spans distances beyond comprehension. The fact that we haven't seen a change doesn't mean it can't happen. Testing this idea requires extreme precision. Scientists use atomic clocks, the most accurate timekeepers in existence, to measure whether fundamental constants shift over time. These clocks rely on the vibrations of atoms, and any tiny change in fundamental physics would show up in how they tick. So far, no shifts have been detected, but researchers continue to refine their methods, pushing the limits of what we can measure. If constants do change, we would have to rethink the foundation of physics. Theories like relativity and quantum mechanics rely on these values staying the same. If they turn out to be flexible, we may need a deeper theory that explains why they change and what governs them. This could lead to breakthroughs in understanding space, time, and the forces that shape the universe. Some physicists think that what we call constants might not be fundamental at all. Instead, they could emerge from deeper principles we don't yet understand. Just as temperature is an average measure of particle motion, fundamental constants could be averages of more complex interactions. If that's true, then changes in these deeper interactions could make constants appear to vary over time. The search for answers continues. New telescopes, more precise experiments, and deeper theories may eventually reveal whether the laws of physics are truly fixed. Until then, we can only test, observe, and question the nature of the universe. If physical constants are not constant, then reality itself may be more dynamic than we ever imagined. Quantum mechanics and general relativity are two of the most successful theories in physics. Each explains a different side of reality. Quantum mechanics describes the behavior of very small things, like atoms and electrons. General relativity explains how gravity shapes space and time on a large scale, from planets to galaxies. Both theories have been tested many times and always seem to work, but when we try to put them together, they don't fit. Imagine a universe made of puzzle pieces. Quantum mechanics is one piece, and general relativity is another. Each fits perfectly with the data we have, but they refuse to lock together. This creates a deep problem in physics. Since everything in the universe follows the same physical laws, we expect one set of rules to describe everything. Right now, we don't have that. Instead, we have two different sets of rules, each working in its own domain, but breaking down when they meet. To understand why this happens, think about how each theory describes reality. Quantum mechanics is built on uncertainty. It says we can never know both the exact position and momentum of a particle at the same time. This is called Heisenberg's uncertainty principle. It means that, at a fundamental level, nature is unpredictable. If you zoom in on a tiny region of space, you find that particles flicker in and out of existence. Empty space isn't really empty. It's full of energy fluctuations that create short-lived particles. General relativity, on the other hand, is built on smooth, continuous space and time. It treats gravity as the bending of space caused by mass. A planet, for example, bends space around it like a heavy ball resting on a stretched rubber sheet. This curvature tells objects how to move. The more mass an object has, the more it bends space, and the stronger its gravity becomes. General relativity assumes that space and time form a smooth fabric without sudden jumps or randomness. The problem appears when we try to describe gravity at very small scales, where quantum mechanics dominates. If we shrink down to a tiny point, like inside a black hole or at the moment of the Big Bang, general relativity predicts infinite density. This makes no sense physically. At the same time, quantum mechanics tells us that space is not smooth but constantly shifting due to energy fluctuations. If we apply general relativity here, we get contradictions. The math breaks down, and we get nonsense answers like infinities where there shouldn't be any. One of the biggest conflicts happens when we try to describe black holes. General relativity predicts that black holes have an event horizon, a boundary from which nothing can escape. But quantum mechanics says that particles can pop in and out of existence near this horizon. This leads to Hawking radiation, a slow leakage of energy that eventually causes a black hole to evaporate. If this is true, it creates a puzzle. What happens to the information that fell into the black hole? General relativity says it's lost forever. Quantum mechanics says information can never be destroyed. This is called the black hole information paradox, and physicists still don't know how to solve it. Another place where the two theories clash is in the early universe. The Big Bang theory, based on general relativity, says the universe started from a singularity, an infinitely small and dense point. But singularities don't make sense in physics. If we had a quantum theory of gravity, it might show that the early universe didn't begin from a true singularity, but from something else. Maybe a quantum fluctuation or a different kind of beginning that avoids infinite density. Without a working quantum theory of gravity, we don't know. Physicists have tried to merge these two theories. One idea is string theory. Instead of treating particles as points, it describes them as tiny vibrating strings. These strings exist in extra dimensions beyond the three of space and one of time that we experience. In string theory, gravity emerges naturally in a way that is more compatible with quantum mechanics. But string theory has not yet been tested, and it requires mathematical assumptions that may not match reality. Another approach is loop quantum gravity. This theory suggests that space itself is made of tiny loops, like a woven fabric, instead of being smooth. This could explain how space behaves at the smallest scales and might help avoid the singularities that general relativity predicts. However, like string theory, it has not yet been proven by experiments. Despite these efforts, we still lack a complete theory that unifies quantum mechanics and general relativity. Some physicists believe we may need a totally new way of thinking about space, time, and gravity. Others think that one or both of these theories might be incomplete, and new discoveries will show us a better way to describe reality. The search for a theory of quantum gravity is one of the biggest open problems in physics. It matters because it could answer deep questions about the universe. What really happens inside a black hole? What was the true nature of the Big Bang? Is space made of something more fundamental? These questions remain unanswered because we don't yet have a single framework that explains everything. For now, quantum mechanics and general relativity remain like two rulers that measure different things. One works for the very small, the other for the very large, but they refuse to work together. the search for a unified theory continues, and until we find it, our understanding of the universe will remain incomplete. Consciousness is the most familiar thing in the world. Every waking moment, you are aware of thoughts, sensations, and emotions. You feel warmth on your skin, see colors, hear music, and taste food. These experiences are part of being alive, but no one knows why they happen. The brain is made of cells. Cells interact through electrical and chemical signals. But how does that create the experience of being? Scientists can explain how the brain processes information. They can map which parts of the brain activate when you see red, feel pain, or hear a melody. But there is something missing from this explanation. Knowing how the brain works does not explain why those processes produce conscious experience. This is the hard problem of consciousness. To understand it, imagine a scientist who has spent her entire life in a black and white room. She has never seen color, but she is an expert in vision. She knows everything about the physics of light, the biology of the eye, and how the brain processes color. One day, she steps outside and sees a red apple for the first time. In that moment, she learns something new, what red looks like. Before, she knew all the facts about color, but she had never experienced it. This shows that there is something about consciousness that facts alone do not explain. The problem gets more puzzling when you consider machines. A computer can process images, recognize faces, and even describe what it sees. But does it experience anything? If a robot looks at a sunset, does it see beauty? Does it feel anything at all? Most would say no. Yet the brain is also a kind of machine, made of physical parts following physical laws. If consciousness is just processing information, why don't computers have it? One answer is that consciousness might be an illusion. Some scientists argue that the brain only feels like it has an inner world. They say consciousness is just a byproduct of thinking, like steam rising from a train. But this idea raises a problem. Illusions happen inside consciousness. If consciousness itself is an illusion, who or what is being fooled? Another theory says consciousness is an emergent property. Just as water's wetness comes from many molecules interacting, consciousness might emerge from the complexity of the brain. But this does not explain why it feels like something to be conscious. Wetness can be explained by the way water molecules stick together. Consciousness has no such explanation. Some scientists believe consciousness depends on specific brain structures. They look for patterns of neural activity linked to awareness. This research has practical uses, such as identifying consciousness in coma patients. But it still does not solve the hard problem. Finding the brain areas that create consciousness is not the same as explaining why those areas produce experience. A different view is that consciousness might not be created by the brain at all. It might be a fundamental part of reality, like space and time. Some physicists suggest that consciousness is woven into the fabric of the universe. Others propose that the brain acts more like a receiver, picking up consciousness rather than generating it. These ideas are speculative, but they show how deep the mystery goes. Another perspective comes from studying split-brain patients. In some surgeries, the connection between the left and right brain hemispheres is cut. This prevents communication between the two halves of the brain. In these patients, each hemisphere appears to have its own awareness. One hand might button a shirt while the other unbuttons it. One hemisphere might know something the other does not. This suggests that consciousness can divide, but if it can split, what holds it together in a normal brain? And if two consciousnesses can exist in one brain, how do we know there is only one consciousness in each of us? Some thinkers explore the possibility that consciousness is everywhere in some form. This idea, called panpsychism, suggests that even simple things like atoms have tiny elements of experience. A single electron would not have thoughts, but if enough particles combine in the right way, they might produce a mind. This avoids the problem of explaining how unconscious matter suddenly becomes conscious. Instead, it suggests that consciousness was always present, just in simpler forms. But if everything has some level of consciousness, why does a rock not seem to think? Why does a tree not talk? One possibility is that complex structures like the brain organize consciousness in a way that creates thoughts and emotions. A rock's atoms may have some awareness, but they are not connected in a way that allows for a mind. Other theories focus on quantum mechanics. Some scientists believe consciousness and quantum physics are linked. The famous double-slit experiment shows that a particle behaves differently when it is observed. Some suggest this means consciousness plays a role in shaping reality. If true, this would mean the mind is not just a product of the brain, but an active participant in the universe. No one has a definitive answer to the hard problem of consciousness. It remains one of the deepest mysteries of science and philosophy. Some believe we will never solve it. Others think a breakthrough is possible, but only if we change how we think about reality. If we do, we may finally understand why it feels like something to be alive. Free will is the idea that people make choices based on their own decisions, not because something else forces them to. It means that when you decide what to eat, where to go, or what to say, you are in control. But are you really? This question has puzzled philosophers, scientists, and thinkers for centuries. Some argue that free will is real and fundamental. Others believe it is an illusion, a trick of the mind that makes us feel in control when we are not. One way to think about free will is to imagine standing in front of a vending machine. You have coins in your hand and a row of snacks in front of you. You can pick anything. You stare at the options. Maybe you choose chips. Maybe you pick a chocolate bar instead. It feels like you made the decision freely. No one forced you. But what if your choice was actually determined before you even reached the machine? Scientists studying the brain have found something strange. In experiments where people are asked to make simple choices, like pressing a button with their left or right hand, brain activity starts before they are even aware of their decision. This suggests that the brain prepares to act before the person consciously decides. If the choice is made before you realize it, are you truly in control? A neuroscientist named Benjamin Libet conducted a famous experiment in the 1980s. He asked people to move their wrists whenever they felt like it while watching a clock. At the same time, he measured their brain activity. What he found was surprising. Brain signals that controlled movement began before the person was aware of wanting to move. It was as if the brain made the decision first, and then the mind caught up. This led some scientists to argue that free will is an illusion. The brain decides, and then we feel as if we made the choice ourselves. But is that really the case? Some argue that these experiments only apply to small, quick decisions and don't tell us about bigger choices, like choosing a career or deciding whether to help someone in need. When making more complex decisions, we take time to think, weigh our options, and reflect on consequences. That doesn't seem like something that happens automatically. Imagine you are walking down a street and see someone drop their wallet. You pause. You could pick it up and return it, or you could keep it. This decision involves memory, social values, and a sense of morality. If free will is an illusion, then your decision would already be determined by your past experiences, brain chemistry, and environment before you even become aware of it. But many people feel that in moments like this, they are making a real choice. Some scientists argue that what we call free will is actually just a feeling. The mind creates a sense of control after the brain has already acted. If true, this would mean that everything we do is determined by biology and physics. In this view, every thought, decision, and action is the result of chemical and electrical signals in the brain, shaped by genes and past experiences. If someone knew enough about your brain and all the experiences that shaped you, they could predict every decision you would make. On the other hand, others argue that free will exists because we can change. We can reflect on our past actions, learn from mistakes, and make different choices in the future. This ability to adapt suggests that we are not simply acting on preset instructions like a machine. There is also the question of randomness. In quantum physics, some events happen without any clear cause. If the world is not entirely predictable at the smallest level, maybe the brain has some level of unpredictability too. But randomness is not the same as free will. If decisions were just random, that wouldn't mean they were truly made by choice. Another perspective comes from philosophy. Some believe that free will and determinism can work together. This idea, called compatibilism, suggests that even if everything is determined by cause and effect, we can still consider ourselves free. as long as we are acting in ways that align with our desires and reasoning. In other words, if you are not forced or coerced, and if your actions follow from your own thoughts and goals, then you are making free choices, even if those choices are influenced by past events. Think about writing an essay. You gather ideas, revise your work, and decide what to include. No one forces your hand, yet every word you choose is shaped by your knowledge, experiences, and language skills. Does that mean you lack free will? Or does it mean your decisions come from who you are, which is what free will really means? The question of free will also has big implications. If everything is determined, should people be held responsible for their actions? If someone commits a crime, was their behavior already set by their biology and upbringing, or did they truly choose to do wrong? This debate affects law, ethics, and how we see human nature. Religious views on free will vary. Many traditions believe that humans have the power to choose between right and wrong. Others believe that a divine plan guides everything, which raises the question of whether free will can exist alongside destiny. Ultimately, the question of free will remains open. Science shows that the brain plays a big role in shaping our decisions before we are aware of them. But human experience suggests we have the ability to think, reflect, and change. Whether free will is real or just an illusion may depend on how we define it. If free will means making choices without any influence at all, then it may not exist. But if it means making decisions based on reasoning, values, and desires, then it might be the most real thing we have. Life exists all around us, but no one knows exactly how it began. Scientists agree that life started from non-living matter, but they don't know the precise steps. The Earth formed about 4.5 billion years ago. At first, it was a hot, violent place with no oxygen in the air. Over time, it cooled and water gathered on its surface. At some point, the right mix of chemicals came together, and the first simple life forms appeared. How that happened remains one of the biggest mysteries in science. One idea is that life started in the ocean, where conditions allowed simple molecules to build into more complex ones. Some scientists think it began near hydrothermal vents, hot openings on the ocean floor where mineral-rich water flowed. These vents create energy and release chemicals that could help form the first biological molecules. The deep sea is still home to life forms that survive in extreme heat and complete darkness, which suggests that early life may have thrived in similar conditions. Another idea is that life started in shallow pools. When water evaporated, it left behind concentrated chemicals. If the right ones were present, they may have joined together to form something more complex. Sunlight, lightning, or heat from volcanoes could have triggered reactions that made the first building blocks of life. These molecules, like amino acids and nucleotides, are essential for living things today. Scientists have shown that they can form naturally under conditions similar to those of early Earth. Some researchers believe that life may have started in space. Meteorites have been found with amino acids, the basic units of proteins. This raises the possibility that simple organic molecules formed in space and arrived on Earth through impacts. If that's the case, life's ingredients may be widespread in the universe. But even if these molecules came from space, they still had to go through additional steps to form living cells. The challenge is understanding how simple chemicals turned into something that could copy itself. All living things contain information stored in molecules like DNA or RNA. These molecules allow life to pass traits from one generation to the next. Scientists think that RNA may have played a key role at the start. Unlike DNA, RNA can both store information and help chemical reactions take place. If early Earth had an abundance of RNA, some of these molecules may have started copying themselves. Over time, errors in copying could have led to variation, and the most stable forms may have continued. For life to begin, molecules also needed to be contained. If chemicals floated freely in water, they would mix and break apart. Something had to keep them together long enough for reactions to take place. Simple cell-like structures may have formed when fatty molecules surrounded water, creating tiny bubbles. These bubbles could trap RNA and other molecules, allowing them to interact without being lost. Modern cells still use membranes made from similar molecules. No one knows how long it took for simple molecules to become the first living cells. could have been a slow process, taking millions of years, or it might have happened in bursts when conditions were just right. Once cells formed, they had to survive and grow. Over time, they may have found ways to use energy from their surroundings, either from sunlight or chemical reactions. Eventually, they evolved into more complex forms, leading to all the life we see today. The search for life's origin is still ongoing. Scientists study ancient rocks to look for the earliest signs of life. They also conduct experiments to see how simple molecules behave under different conditions. Space missions explore other planets and moons, looking for places that might have supported life in the past. If scientists find evidence of life elsewhere, it could help explain how it started here. Understanding the origin of life is difficult because there is no way to go back and watch it happen. The best scientists can do is recreate conditions in the lab and look for clues in nature. They have made progress in understanding how life's building blocks could have formed, but the leap from simple molecules to the first cells remains a mystery. The answer, when it comes, will change our understanding of life, not just on Earth, but throughout the universe. Imagine waking up one day and realizing that everything around you, your friends, family, the sky, even your own thoughts, could be part of a vast computer program. This idea might sound like something from a science fiction movie, but it is a serious question that some scientists and philosophers have considered. The idea that reality might be a simulation is not just speculation. It comes from real observations about the nature of the universe and the way information behaves at a fundamental level. Think about video games. Decades ago, games were just a few pixels on a screen. Now they have complex worlds, realistic physics, and characters that react in ways that seem almost human. Every year, the line between real and artificial gets thinner. If technology keeps advancing, it seems likely that one day we will create simulations that are so real, the people inside them won't know they are in a game. If that's possible, then how do we know it hasn't already happened? The idea comes largely from philosopher Nick Bostrom, who proposed a simple argument. He suggested that if any civilization ever reaches a point where it can create realistic simulations of consciousness, then it will probably create many of them. If that's true, then simulated minds could far outnumber real ones. If that's the case, what are the chances that we are among the rare real ones instead of the countless simulations? Based on probability alone, the answer might be that we are already inside one. There are reasons why this theory makes sense. The laws of physics behave in ways that look suspiciously like code. In computers, everything boils down to bits of information, ones and zeros. Strangely, physicists have found that the fundamental laws of the universe also seem to be based on information. Quantum mechanics, the branch of physics that deals with tiny particles, shows that reality only decides what something is when it is observed. Before that, particles exist in a state of probability, like an undecided piece of data. This is very similar to how a video game only renders what's on the screen when you look at it. When you turn around, the game doesn't waste resources rendering the parts of the world you aren't seeing. If the universe worked the same way, it would be a strong sign that it behaves like a simulation. Another strange discovery is the way reality has limits. In a computer simulation, the level of detail can only go so deep before you hit the smallest possible unit, the pixel. In our universe, scientists have discovered that space, time, and even energy are not continuous. They exist in tiny, discrete units, as if the universe itself has a resolution limit. If reality were truly infinite and not simulated, we might expect it to be smooth all the way down, rather than built from tiny building blocks. Even the way we experience reality suggests something artificial. The human brain can only process so much information at once. When we focus on one thing, we tend to ignore everything else. Our memories are unreliable. We don't store every moment of our lives in high detail. Instead, our brains take shortcuts, filling in gaps to make sense of the world. If we were in a simulation, that's exactly how we might expect it to work, only rendering and storing the details that are necessary while letting the rest fade away. Some scientists have tried to test the theory. If the universe were a simulation, it might have glitches. One idea is that cosmic rays, the high-energy particles that come from space, should be able to hit Earth from any direction. But some research suggests they only come from certain angles, as if they are constrained by an underlying system. This could mean the universe has a processing limit, like a simulation struggling to keep up with too many calculations at once. If we are in a simulation, who built it? That question is harder to answer. Some think it could be a future version of humanity, running simulations of their ancestors. If so, our reality might be a way for them to study history or test different scenarios. Others think it could be an advanced alien civilization. There is even a possibility that the simulation itself is not run by a biological being at all, but by an artificial intelligence so advanced that it manages entire realities. If this idea is true, does it change anything? For most people, daily life would still be the same. You would still have to wake up, go to work, and pay bills. But on a deeper level, it raises interesting questions. If we are in a simulation, does that mean free will is an illusion? If someone or something created this world, does that mean there is a purpose behind it? Could we ever escape? And if the simulation ends, what happens to us? Not everyone agrees with the simulation theory. Some argue that just because we could one day build realistic simulations, it doesn't mean we already live in one. Others point out that if the universe were simulated, we should have found clear evidence by now. Even though there are strange patterns in physics, that doesn't prove they come from a computer program. Reality could simply be built on mathematical rules that we don't fully understand yet. Another issue is the sheer amount of computing power needed. If our universe is a simulation, it is incredibly complex. The amount of information needed to keep track of every particle, every atom, and every human thought would be beyond anything we can imagine. Some say that even an advanced civilization might not have the ability to run a simulation at this scale. If so, then the idea that we are in one becomes less likely. Despite these doubts, the simulation theory remains an open question. Even if we don't have proof, the possibility alone changes how we think about reality. It forces us to consider what it means to exist and whether the world around us is as real as we assume. If nothing else, it reminds us that reality may not be as simple as it seems. Maybe one day we will find a way to test the theory for certain. If we discover an undeniable glitch in reality, or if an advanced intelligence contacts us and admits that they are running the program, then we will have our answer. Until then, we are left with the mystery and the unsettling possibility that everything we see, hear, and feel is not what we think it is. A single brain usually means a single person, a single mind making decisions and experiencing the world. But in some cases, a brain seems to house more than one awareness, more than one version of self. This idea challenges how we think about consciousness. Can one brain hold multiple separate conscious entities? This question takes us into the study of dissociative identity disorder, DID, the nature of self, and how the brain organizes identity. DID, once called multiple personality disorder, is a condition where a person seems to have two or more distinct identities that take control at different times. These identities, sometimes called alters, can have their own memories, habits, and even ways of speaking. One alter may have no idea what another has done. A person may wake up to find their belongings rearranged, notes written in a handwriting they don't recognize, or strangers greeting them by a name they don't know. These shifts are not acts or imagination. They are real to the person experiencing them. Brain scans show differences in activity when different alters are present, supporting the idea that something distinct is happening. People with DID often report a history of severe trauma, usually in childhood. The theory is that their young mind, overwhelmed by pain, created mental barriers. Instead of one cohesive self, different parts split off to handle different experiences. One part might take the pain, another might carry anger, and another might hold everyday memories. Over time, these parts develop their own voices, behaviors, and perspectives, becoming distinct identities. This is not like playing different roles or putting on a social mask. It is a deeper division, one where each identity experiences itself as separate from the others. For a person with DID, switching between alters is not like changing moods. It can be sudden, unexpected, and disorienting. One moment, they might be in control, The next, another identity has taken over, and they have no memory of the transition. Some alters are aware of each other, like roommates in the same house. Others are completely cut off. Some may dislike or even fear each other. This fragmentation raises an unsettling question. If one brain can hold multiple identities that feel separate, does that mean multiple conscious beings exist within one person? Consciousness is hard to define. We know we are aware because we experience thoughts, feelings, and sensations. But how do we know where one consciousness begins and another ends? In DID, each identity seems to have its own stream of thoughts, its own history, and its own perception of the world. If they do not share memories or awareness, are they separate consciousnesses? Or are they different aspects of one larger consciousness, split but still part of the same whole? Science does not have a clear answer. Some researchers argue that each alter is not a fully separate consciousness, but rather a dissociated piece of the same mind. They compare it to a broken mirror. The reflections look different, but they all come from the same original piece. Others suggest that because each alter has a distinct sense of self, each one may count as its own conscious being. This would mean that a single brain could house multiple minds, each as real as the next. DID is not the only condition that raises these questions. Some cases of brain damage or surgery suggest that consciousness can split in surprising ways. People with split brain syndrome, caused by cutting the corpus callosum, the bridge between the brain's two halves, sometimes show signs of two separate streams of awareness. If a person sees an object only with the left eye, they might not be able to name it, since the left side of the brain controls speech. But if asked to draw it with their left hand, they can, as if part of them knows what the object is, even if they cannot say it. This suggests that each hemisphere has its own independent processing, almost like two minds in one head. Even in everyday life, we experience moments that hint at multiple selves. People sometimes talk about feeling torn between choices, as if two parts of their mind argue with each other. Some describe acting without thinking, and later feeling like someone else made their decisions. These are not the same as DID, but they show that our sense of self may not be as unified as it seems. If multiple consciousnesses can exist in one brain, what does that mean for identity? We tend to think of ourselves as a single person with a continuous past. But if our brain can divide into different awarenesses, is identity just a story we tell ourselves? If someone with DID integrates their alters, do those alters cease to exist, or do they merge into a greater whole? If a split-brain patient has two independent streams of thought, are they two people inside one skull? These questions challenge our understanding of the self. If consciousness is not tied to one single, unbreakable identity, then it might be more fluid than we assume. This has implications beyond DID or brain injuries. Could artificial intelligence develop multiple streams of consciousness? Could a future brain-machine interface allow one person to share awareness with another? If we ever upload our minds to a computer, would copies of us be separate people, or just extensions of oneself? For now, the question remains open. People with DID experience their alters as real, separate individuals, even if science struggles to define them as such. Split brain studies suggest that awareness can divide under the right conditions. And our own daily experiences hint that the self is more complex than a single, unified whole. Whether this means multiple consciousnesses can truly exist in one brain depends on how we define consciousness itself. Until we understand that, the nature of self will remain one of reality's greatest mysteries. Memory is one of the most fascinating and complex functions of the human brain. Some moments stay with us for years, while others vanish within seconds. A childhood birthday party might feel as vivid as yesterday, but the name of someone you just met can slip away in an instant. Understanding why this happens requires looking at how memory is formed, stored, and retrieved. The brain takes in a constant stream of information. Every sound, sight, smell, and thought moves through a network of neurons. But not everything sticks. The brain decides what to keep and what to discard based on attention, emotion, and repetition. If something seems important, the brain works to store it. If not, it fades. Memory works in stages. The first is sensory memory, which holds raw data for a fraction of a second. This is what lets you register a face, a voice, or a smell before deciding if it matters. Most of this information disappears almost instantly. The next stage is short-term memory, where the brain keeps information for a brief time. When you hear a phone number and repeat it to yourself to dial, that's short-term memory at work. Without reinforcement, the brain clears out this storage space quickly. Some information moves into working memory, which allows you to process and manipulate it. When you do mental math or follow directions, your working memory helps you hold and use that information. Long-term memory is where things get interesting. Some memories last for days, others for decades. The brain strengthens long-term memories based on several factors. One of the strongest influences is emotion. When something triggers a strong emotional response, the brain takes extra steps to encode it. This is why people remember exactly where they were when they heard shocking news, but forget what they had for lunch last Tuesday. The brain sees emotional events as more important and makes them easier to recall. Repetition also plays a role. The more the brain revisits a piece of information, the stronger the memory becomes. This is why studying over time works better than cramming. A single exposure to a fact might not stick, but seeing it multiple times tells the brain it matters. This process, called consolidation, strengthens neural connections, making recall easier later. Memory is not like a filing cabinet where each fact sits in a specific drawer. It is more like a web with pieces of information connected in different ways. When you remember something, your brain reconstructs it from fragments. This means memories are not always exact copies of what happened. They can change over time, influenced by new experiences, emotions, or even suggestions from others. One reason we forget things quickly is that the brain constantly clears out unneeded information. This prevents overload and keeps space available for new details. If the brain held on to every small piece of data, recalling anything useful would be nearly impossible. Forgetting is not a failure. It is an active process that helps keep the most relevant information accessible. Attention plays a big role in what we remember. If your mind is elsewhere when someone introduces themselves, their name never fully enters your memory. The brain filters out distractions to focus on what seems important. This is why people who multitask often struggle to recall details later. If information does not get proper attention, it does not get stored. Memories can also be unreliable. The way the brain reconstructs past events means that details can change. If someone tells a story repeatedly, they might unconsciously alter small pieces each time. Over years, these small changes add up, and the memory becomes different from the original event. This happens to everyone, not just in dramatic ways, but in small, everyday experiences. This is why two people can remember the same event differently, each convinced they are right. Sleep is critical for memory. During deep sleep, the brain sorts and strengthens memories, deciding what to keep and what to let go. Poor sleep makes it harder to form new memories and weakens recall of old ones. People who study right before bed often remember things better because the brain works on that information overnight. The environment also affects memory. Familiar settings and repeated routines make recall easier. If you always put your keys in the same spot, finding them becomes automatic. But if you place them somewhere new without paying attention, you might struggle to remember where they are. This is because the brain links memories to context. Walking back into a room can trigger recall of why you went there in the first place. Some memories seem locked away, yet a single trigger can bring them back in vivid detail. A song from childhood, a familiar smell, or an old photograph can unlock memories thought forgotten. This happens because the brain stores memories in networks that can reactivate with the right cue. Forgetting can also be useful. Traumatic memories sometimes fade as a protective measure. The brain has mechanisms to suppress painful or distressing memories to help people move on. However, strong emotions can also make bad memories stick. This is why people with post-traumatic stress disorder, PTSD, struggle with intrusive memories. Their brain holds on to those moments too tightly, replaying them when triggered. Age affects memory, but not always in the ways people expect. The brain naturally becomes less efficient at processing new information as it ages, but long-term memory often remains strong. Older adults may struggle with names or recent events, but recall childhood experiences with clarity. This happens because different types of memory rely on different brain structures, some of which decline faster than others. Technology changes how people use memory. With smartphones storing phone numbers, addresses, and reminders, the brain no longer has to remember them. This shifts the way memory functions, making people rely more on external storage. While convenient, it also means that the brain gets less practice in recall, which can make natural memory weaker over time. Memory is not perfect, but it is an incredible tool. It allows people to learn, adapt, and build personal histories. While some things fade, the brain holds on to what seems most useful, shaping how people experience the world. By understanding how memory works, people can take steps to strengthen it, making the most of the brain's ability to remember. Death is the one thing every person will face, yet no one knows exactly what happens when it comes. It is the point where everything familiar, the body, the mind, the sense of self, seems to stop. But does anything continue? That question has haunted humans for as long as we have been able to ask it. The body is easy to explain. When the heart stops beating, blood stops flowing. Cells begin to die, first in the brain, then in the rest of the body. Within minutes, the brain runs out of oxygen, and the electrical signals that create thoughts and memories fade away. From a biological perspective, this is the end. Everything that made a person who they were, their personality, their emotions, their decisions, seems to depend on a working brain. When that brain stops, those things disappear. That explanation satisfies science, but it does not answer the deeper question. People do not experience their own bodies shutting down. They experience thoughts, emotions, and perceptions. The question is whether that experience continues in some way after death. Many believe it does. Many believe it does not. No one knows for sure. Some say death is like falling asleep forever. If a person does not exist before birth, why should they exist after death? From this view, consciousness is tied to the brain. If the brain is gone, there is no more experience, just like there was nothing before a person was born. This is a simple answer, but it has a problem. People do not know what it is like to not exist. Sleep is not a good comparison because even in deep sleep, the body is still alive and the brain is still active. The idea of an empty, eternal nothing is impossible to imagine because a person can only experience something. Others believe the mind is separate from the body and continues after death. This belief appears in nearly every culture and religion. Some think of it as a soul that moves on to another realm, whether that is heaven, reincarnation, or some other form of existence. Others believe in a kind of energy that does not disappear, but instead changes form. People who have had near-death experiences describe floating outside their bodies, seeing a bright light, or meeting deceased loved ones. These stories suggest that consciousness might exist without a body, though skeptics argue that the brain, when deprived of oxygen, can create strange and powerful hallucinations. Science has not proven or disproven an afterlife. It cannot study what happens after death because, by definition, death is the point where observation stops. The closest thing to evidence comes from people who have been revived after being clinically dead. Some of them report seeing or feeling something, but their experiences are not consistent. Some describe peace and light. Others describe nothing at all. If the afterlife were real, would it not be the same for everyone? If it is a trick of the brain, why do so many people report the same kinds of visions? Physics complicates the question. The body and brain are made of atoms, and atoms do not disappear. Energy does not vanish, it only changes. But does that apply to consciousness? Thoughts and memories are patterns of electrical activity, and when the brain dies, those patterns stop. No one knows if something beyond the physical world holds on to them. Some turn to quantum mechanics for answers. In the strange world of tiny particles, reality is not as solid as it seems. Some theories suggest that consciousness is connected to the fabric of the universe itself. If true, death might not be the end, but a transition. Others argue that this is just speculation, that quantum physics does not say anything about what happens after death. Another possibility is that reality is not what it seems at all. Some scientists and philosophers suggest that consciousness creates reality, not the other way around. If that is true, Death might not mean the end of experience, only a change in how experience happens. Perhaps life and death are both illusions, and what lies beyond is something entirely different from what we expect. Some people claim to have memories of past lives. They recall names, places, and events that they should not know. Some of these cases are difficult to explain, but they are rare. Most people do not remember anything before birth, which suggests that if reincarnation happens, it does not preserve personal identity. If a person's consciousness moves on to another life, but they remember nothing, is it still the same person? Many religions teach that what happens after death depends on how a person lived. Christianity speaks of heaven and hell. Hinduism and Buddhism describe karma and rebirth. Other traditions believe the dead become spirits, ancestors, or part of a greater whole. These beliefs shape how people live and how they face death. But no one has come back with proof. Faith is not the same as knowing. One thing is certain: death is not the same for everyone. Some die in fear, others die at peace. Some slip away without pain, while others struggle. The way a person approaches death often depends on what they believe about it. Those who think death is the end may see it as a return to nothingness, neither good nor bad. Those who expect something beyond often take comfort in the idea that life continues in another form. Perhaps the mystery of death will never be solved. Perhaps it is not meant to be solved. If people knew for certain what came next, would it change the way they live? Would they stop fearing death? Would they chase after it? Maybe the unknown is necessary. For now, death remains the greatest mystery. It is the boundary that no one can cross and return from unchanged. The only certainty is that one day, every person will find out the answer for themselves. Until then, all we have are questions, theories, and the way we choose to live with the mystery. In the world of physics, there is a strange phenomenon called the observer effect. It suggests that the act of measuring something can change what is being measured. This is most famously demonstrated in quantum mechanics, where the behavior of particles shifts depending on whether or not they are being observed. This raises a deeper question. Does consciousness play a role in shaping reality? To understand this, consider the double-slit experiment. This experiment involves shooting tiny particles, like electrons, at a barrier with two slits. If no one observes them, they seem to pass through both slits at once, forming an interference pattern on the other side, as if they were waves. But when a measuring device is placed to observe which slit each particle passes through, they behave like solid particles and go through only one slit. The wave-like behavior disappears. The mere act of measurement seems to change how these particles act. This result is unsettling because it suggests that the observer plays a role in the outcome. In everyday life, we don't expect objects to change just because we look at them. A chair remains a chair whether or not someone is in the room. But at the quantum level, things behave differently. This has led some to wonder if consciousness itself influences reality. If an electron behaves differently when observed, does that mean awareness is affecting it? Some scientists argue that the observer effect is not about consciousness at all. Instead, they say it is the interaction of the measuring device with the particle that causes the change. To measure something at the quantum level, scientists must use instruments that interact with the particles in some way, such as shining light on them. This interaction disturbs the system, leading to the change in behavior. In this view, the presence of a conscious observer is not what matters. It is the act of measurement, which requires some kind of physical disturbance. Others are not so sure. The idea that consciousness plays a fundamental role in reality is an old one. Some interpretations of quantum mechanics suggest that particles exist in multiple possible states until someone observes them. This idea, called the Copenhagen interpretation, implies that reality does not take definite shape until it is observed. The famous physicist John von Neumann extended this idea, arguing that only a conscious mind can collapse a quantum wave function. In other words, without consciousness, reality remains in an uncertain, undefined state. This leads to even stranger questions. If observation shapes reality, then who or what was the first observer? Did reality exist before there were conscious beings to witness it? If not, what brought the universe into existence? Some philosophers and physicists have speculated that the universe might be shaped by a cosmic consciousness, or that reality itself might be the result of an ongoing observation by some unknown force. These ideas, while intriguing, remain speculative. Another interpretation that challenges this view is the many worlds interpretation. According to this idea, every possible outcome of a quantum event actually happens, but in separate, parallel universes. In this case, observation does not collapse possibilities into one outcome. Instead, all possible outcomes unfold in different branches of reality. If this is true, then consciousness does not control reality, but merely experiences one of many possibilities. Even if consciousness does not shape reality at the quantum level, the question of what consciousness is remains unanswered. We still do not fully understand how the brain produces subjective experience. Scientists can study the brain's electrical and chemical activity, but they cannot explain why we have thoughts and feelings. This mystery, known as the hard problem of consciousness, makes some wonder if consciousness is something more fundamental than matter itself. If it is, then it might still have a role in how reality works. Some experiments have tried to test whether consciousness affects quantum mechanics. In one study, researchers asked participants to focus their attention on a quantum system to see if their thoughts could influence the results. Some claim to find small effects, but these results remain controversial. Many scientists argue that any such findings are likely due to errors in the experiments rather than evidence that the mind can directly influence physical reality. Despite this, the connection between observation and reality continues to fascinate people. Some thinkers argue that even if consciousness does not affect quantum mechanics, it is still central to our understanding of reality. Everything we know about the world comes through our perception. If we had no conscious experience, we would have no way to describe or understand reality at all. In this sense, reality as we know it is always shaped by consciousness, not because it alters physics, but because it is the lens through which we perceive everything. The debate over the role of consciousness in physics remains unresolved. Some physicists believe that future discoveries in quantum mechanics will eventually remove any need for consciousness in explaining the observer effect. Others think that understanding consciousness will require a completely new framework that goes beyond current science. For now, the nature of observation, measurement, and reality remains one of the deepest mysteries in physics. Even if consciousness does not shape the physical world, it plays a crucial role in shaping human experience. Our thoughts, emotions, and perceptions define the reality we live in every day. Whether or not quantum mechanics depends on consciousness, the way we observe the world influences how we interpret it. This alone makes the observer effect a fascinating topic, one that continues to inspire both scientific inquiry and philosophical reflection. Dreams have fascinated people for centuries. Some see them as random stories our minds create while we sleep. Others believe they hold deeper meaning. Scientists have studied dreams for years, but they still don't fully understand why we have them. Some theories suggest dreams help process emotions or store memories. Others say they serve no real purpose at all. When people fall asleep, their brains don't shut down. Instead, they go through cycles of light and deep sleep. One of these stages is called REM sleep. This is when most dreams happen. During REM sleep, the brain is active almost as much as when awake. The body, however, stays still. The eyes move rapidly, which is why it's called rapid eye movement sleep. If someone wakes up during REM sleep, they're likely to remember their dreams. Some researchers believe dreams help with memory. Throughout the day, the brain takes in a lot of information. Not all of it is useful. The brain needs to sort through this information, keeping what's important and discarding the rest. Some think dreams help with this process. They may be a way for the brain to review events and decide what to keep. People who study memory have found that those who dream about learning something new tend to remember it better the next day. This suggests that dreams might help reinforce learning. Others think dreams are tied to emotions. Life is full of experiences, some good and some bad. Dreams might be the brain's way of making sense of these feelings. When something upsetting happens, a person might dream about it later. The dream might not be an exact replay, but it often carries the same emotions. Some believe this is the brain's way of processing feelings in a safe way. If a person faces fears in a dream, they might feel less afraid of them when awake. Another idea is that dreams are a form of problem solving. People sometimes wake up with solutions to problems they struggled with the day before. Famous examples include scientists and artists who say their best ideas came from dreams. The chemist Friedrich Kekulé dreamed of a snake biting its own tail, which helped him understand the structure of benzene. The writer Mary Shelley got the idea for Frankenstein from a dream. If dreams help people think in new ways, they might serve an important creative function. Some researchers argue that dreams don't have a purpose at all. They believe dreams are just the brain's way of staying active during sleep. Since the brain doesn't receive input from the outside world, it creates its own stories from memories and random thoughts. This would explain why dreams often seem strange or disjointed. If dreams had a clear function, they might be more logical. Despite these theories, many questions remain. If dreams help with memory, why do we often forget them? If they help process emotions, why do people sometimes dream about things that don't seem important? Some dreams repeat, while others never return. Some feel meaningful, while others seem absurd. The variety of dreams makes it hard to pin down one explanation. Lucid dreaming adds another layer of mystery. This happens when people realize they are dreaming and can sometimes control what happens. Some people train themselves to do this, while others experience it by chance. Lucid dreaming raises questions about how aware we are while asleep. If people can think and make choices in a dream, what does that say about consciousness? Nightmares add another question. Why does the brain create dreams that scare us? Some nightmares come from real fears, but others seem random. One idea is that nightmares prepare people for danger. If someone dreams about being chased, they might react faster in a real-life emergency. Another thought is that nightmares are just the brain's way of processing stress. Children have more nightmares than adults, which could mean the brain uses them to help understand the world. A child's brain is still developing, and they experience many new things each day. Their dreams might be a way to sort through these experiences. As people grow older, their dreams change. Some report having fewer nightmares, while others say their dreams become more realistic. Culture also plays a role in how people see dreams. Some societies believe dreams predict the future. Others think dreams connect to the spirit world. In ancient times, leaders sought advice from dream interpreters. Even today, some believe dreams hold hidden messages. Scientists don't support these ideas, but they acknowledge that dreams reflect a person's thoughts and emotions. Technology has allowed researchers to study dreams more closely. Brain scans show what happens when people dream, but they don't explain why it happens. Scientists have tried to decode dreams by tracking brain activity, but results are still unclear. Some hope that future studies will reveal more about the purpose of dreaming. Until then, the question remains open. Dreams could be a tool for learning, a way to handle emotions, or just the brain's random activity. They might serve different functions at different times. While scientists continue to study dreams, people will keep wondering what they mean. People experience life from a first-person perspective. They see the world, think thoughts, and feel emotions in a way that seems personal and unique. This sense of self feels real and constant. But where does it come from? Scientists, philosophers, and psychologists have explored this question for centuries, yet no one has a definitive answer. The sense of self is complex, shaped by the brain, the body, and interactions with the world. Understanding it requires looking at how the mind builds identity, how memory plays a role, and how the body contributes to the experience of being an individual. The brain processes countless pieces of information every second. Some of these come from the outside world, sights, sounds, smells, and touches. Others come from within, thoughts, memories, and emotions. The brain organizes this information into a coherent experience. It does this so well that it feels seamless. The self appears to be a single entity, but in reality, it is a construction of different mental processes working together. One major part of the self is the ability to recognize oneself as distinct from everything else. A person can look in a mirror and know, without thinking that the reflection is their own. This ability is not automatic for all creatures. Babies do not recognize themselves in mirrors until they are about 18 months old. Some animals, like dolphins and elephants, show signs of self-recognition, but most do not. This suggests that the sense of self is something that develops over time, rather than being present from birth. Memory plays a key role in shaping identity. People remember their past experiences, which gives them a sense of continuity. If someone could not remember anything from one moment to the next, they would struggle to feel like the same person over time. Consider how people with amnesia sometimes lose their sense of self. If someone forgets their past, they often feel lost. They might not recognize their own name or the people they love. Without memory, the self can disappear. Thoughts and emotions also contribute to the feeling of being an individual. A person has opinions, preferences, and beliefs that make them feel unique. If someone loves chocolate ice cream and hates horror movies, that becomes part of their identity. If they change their mind over time, they might still feel like the same person, even as their tastes shift. This shows that the self is flexible but remains consistent in important ways. The body also plays a major role in shaping the self. People have a physical form that they identify as their own. If someone closes their eyes and moves their hand, they know where it is without looking. This sense, called proprioception, helps create the feeling of being in a body. When someone loses a limb, they often experience a phantom limb, where they still feel like the missing part is there. This suggests that the brain has a built-in map of the body that contributes to the sense of self. Social interactions influence the way people see themselves. From an early age, individuals learn who they are by how others react to them. A child who is often praised for being kind may come to see themselves as a kind person. Someone who is told they are funny may embrace that as part of their identity. The self is not just something that comes from within. It is also shaped by relationships and society. This can change over time, especially if someone moves to a new place or takes on a new role. Cultural differences can affect the sense of self as well. In some cultures, people see themselves as independent individuals. They focus on their personal achievements and goals. In other cultures, people see themselves as part of a group. They define themselves by their family, community, or social role. Neither way is right or wrong, but these perspectives show that identity is not just biological, it is also shaped by upbringing and environment. The question of whether the self is real in an objective sense is still debated. Some scientists argue that the self is an illusion created by the brain. They point out that there is no single part of the brain responsible for identity. Instead, many different regions work together to create the experience of being a person. This does not mean the self is meaningless, just that it is a mental construct rather than a fixed thing. Neuroscience has shown that damage to the brain can change personality and identity. One famous example is Phineas Gage, a railroad worker in the 1800s. After an accident sent an iron rod through his skull, he survived but became a different person. His friends said he was no longer himself. This suggests that the self is tied to the brain's physical structure. If the brain changes, the self can change too. Modern research on split-brain patients provides further insights. In some cases, doctors have severed the connection between the left and right halves of a person's brain to treat severe epilepsy. After this, patients sometimes show signs of having two separate selves. One hand might start a task while the other undoes it. In some cases, a patient could draw different shapes with each hand at the same time, something most people cannot do. This suggests that the brain creates a unified self by linking different processes. When that connection is broken, the unity of the self can break down as well. Despite these findings, most people experience a strong and stable sense of identity. Even though personalities evolve over time, there is a feeling of continuity. This might be because the brain naturally creates a story about who a person is. Memory, perception, and emotion come together to maintain a narrative of selfhood. The sense of self is essential for daily life. It helps people make decisions, form relationships, and navigate the world. Without it, everything would feel chaotic and disconnected. While science has made progress in understanding how the self works, many questions remain. Why does the brain generate this experience in the first place? Could a machine ever develop a sense of self? If so, what would that mean for the nature of identity? These mysteries continue to fuel research and debate. In the end, the self is both simple and complex. It feels natural and automatic, yet it depends on a web of mental processes. It comes from the brain, but it is shaped by experiences, relationships, and culture. Though researchers have uncovered many clues, the full answer remains elusive. The sense of self is a puzzle, one that each person experiences in their own way, every moment of their lives. Mathematics works surprisingly well in describing the universe. We use numbers, equations, and formulas to explain everything from the motion of planets to the way atoms behave. This raises a big question: why? Why does math, a system we create in our minds, match reality so perfectly? This has led to a long debate about whether math is something we discover or something we invent. Imagine a world without humans. Planets would still orbit stars, and waves would still crash on the shore. The patterns we see in nature, the way an apple falls from a tree or the symmetry of a snowflake, would still exist. But without people to describe them, there would be no numbers, no equations, no theorems. The laws of physics would still be there, but the symbols we use to describe them would not. This makes it tempting to say that math is just a tool we invented to understand the world, rather than something that exists on its own. But this explanation has problems. Take prime numbers. These are numbers that can only be divided by one in themselves. They follow patterns that seem random, but over time, mathematicians have uncovered deep structures within them. No one created prime numbers. They exist whether we write them down or not. Some patterns in prime numbers have only been found recently, yet they seem to have been there all along, waiting to be discovered. This suggests that math is not just something we make up. It seems to have an independent existence, as if we are uncovering truths rather than creating them. Physics gives more examples. Einstein's equations predicted black holes long before anyone had seen one. When scientists first worked out the math behind general relativity, black holes seemed like a strange and unlikely result. It took decades before we found real evidence that they existed. The math was right before we had any proof. This happens often in science. Equations predict things that later turn out to be real. In quantum mechanics, Paul Dirac's equations predicted antimatter. No one had ever seen antimatter, and no one had expected it, but the math led the way. Years later, scientists found real antimatter in experiments. If math were just something humans invented, this wouldn't make sense. It would be like creating a board game and then realizing later that the rules of the game match the way the real world works. That seems unlikely. Instead, it looks like math is something deeper, something we are uncovering rather than making up. But there's another way to look at it. Math is full of things that don't seem to exist in nature. There are infinite numbers, imaginary numbers, and strange geometries that don't match anything we see around us. We can create mathematical objects that have no physical counterpart. Some mathematicians work on abstract problems for centuries without any connection to reality. Later, physicists sometimes find that these strange mathematical ideas happen to describe the real world, but there are also many mathematical ideas that never find any application in science. If math were truly something that exists independently of us, wouldn't all of it describe the universe? Maybe the reason math works so well in physics is because we have shaped it to fit. Over time, we have refined our mathematical tools to match what we see in nature. If one kind of math doesn't work, we try another until we find one that does. This would mean math is more like a language than a set of universal truths. The word tree exists in English, Spanish, and Chinese, but the tree itself is independent of language. Different cultures might come up with different words for it, just like different civilizations might describe the universe using different kinds of math. Still, even if math is a language, it is an incredibly powerful one. No matter who discovers a mathematical truth, it always seems to hold. A civilization on another planet, if advanced enough, would likely find the same basic mathematical rules. They might use different symbols, but their understanding of numbers, geometry, and physics would have to match ours. They would know about prime numbers because prime numbers exist no matter what you call them. They would find the same solutions to problems in physics because the laws of the universe are the same everywhere. This suggests that math is more than just a tool. It seems to be something woven into the fabric of reality. But does that mean it was always there, waiting to be found? Or is it something that only takes shape once an intelligent mind starts to think about it? If math exists independently, it raises strange questions. Where do mathematical truths exist? A physical object exists in space. A thought exists in a person's mind. But mathematical truths don't seem to exist in either place. The Pythagorean theorem is always true, even if no one is thinking about it. If there were no minds in the universe, would mathematical truths still exist? If math is something we discover, then it must exist somewhere. But where? On the other hand, if math is something we invent, why does it work so well? Why does the universe follow rules that we just happen to create? If our brains had evolved differently, would we have come up with an entirely different kind of math? And if so, would that math still describe the world as well as the one we use? One possible answer is that reality itself has a deep mathematical structure. The universe might not just obey mathematical laws, it might be mathematical at its core. Some physicists have suggested that everything we see, from particles to galaxies, is just a complex mathematical structure. If this is true, then math is not just a tool we use to describe the world, it is the world. But even if this idea is correct, it does not fully answer the question. It only pushes it further back. If reality is math, why is it that way? Why does the universe follow a mathematical pattern rather than something else entirely? Could there be universes where math does not apply? Or is math so fundamental that nothing can exist without it? We do not yet have answers to these questions. What we do know is that math remains one of the most powerful ways to understand reality. Whether we discover it or invent it, math continues to reveal deeper and deeper truths about the universe. And as we explore more, we may find that the line between discovery and invention is not as clear as it seems. Infinity is a concept that appears everywhere, from mathematics to philosophy to physics. People use the word often, but its true nature remains unclear. Is infinity something real that exists in the universe, or is it only a human-made idea? To understand this, we need to look at how infinity appears in different areas of thought. In mathematics, infinity is a well-defined concept. You can think of it as a number that keeps going forever. Imagine counting 1, 2, 3, and so on. No matter how high you count, you can always add one more. That process never stops, which means numbers go on infinitely. But does that mean infinity is something real? A number like 5 represents 5 apples, 5 fingers, or 5 minutes. Infinity, however, does not correspond to a specific quantity of anything. You can never hold infinity apples or experience infinity minutes. Mathematicians have developed ways to work with infinity. For example, a simple fraction like 1 divided by 0 does not produce a regular number. Instead, it is often said to approach infinity. This means that as the denominator gets smaller, the result gets larger without bound. But no matter how close you get, you never truly reach infinity. This idea is useful in calculus, where limits and infinite series help describe change and motion. Even though math relies on infinity, it does not prove that infinity exists in a physical sense. Instead, it serves as a tool to describe things that grow indefinitely. Infinity also appears in physics. The size of the universe, for example, is a major question. Scientists do not know whether the universe is infinite or just extremely large. Some models suggest that space continues forever, without any boundary or edge. If that is true, then infinity is not just a concept, but a real part of existence. On the other hand, some theories propose that the universe loops back on itself in a way that makes it seem endless while still being finite. The problem is that humans have no way of observing the entire universe to confirm either idea. So even in physics, infinity remains uncertain. Another place infinity appears is in the behavior of black holes. According to general relativity, the center of a black hole contains a singularity, a point where gravity becomes infinite. This means that space and time break down, making it impossible to describe what happens there. However, physicists generally believe that this infinity is not real, but instead signals a gap in our understanding. Future discoveries in quantum gravity might show that the singularity is not truly infinite, but just extremely small and dense. This suggests that infinity might often be a sign that something is incomplete rather than something that actually exists. Beyond science, infinity raises deep philosophical questions. If time is infinite, does that mean everything that can happen will eventually happen? Some theories in philosophy suggest that if the universe is infinite, then every possible event must repeat somewhere. This means there could be countless versions of you, each living a slightly different life. But if the universe is finite, then such repetition would never occur. Even in everyday thinking, infinity causes confusion. Imagine a hotel with an infinite number of rooms, known as Hilbert's Hotel. If every room is full and a new guest arrives, you might think there is no space. However, if each guest moves to the next room, room 1 to room 2, room 2 to room 3, and so on, then room 1 becomes available. This paradoxical idea shows how infinity follows different rules from ordinary numbers. It also highlights the difference between potential infinity, something that can keep growing, and actual infinity, something that already exists as infinite. If infinity exists, can it be measured? Physicists and mathematicians have different views. Some argue that since infinity is never reached, it is not real. Others believe that infinity is a necessary concept to explain the universe. For example, if space has no end, then something infinite does exist. Yet, even in that case, infinity remains an abstract property rather than a tangible thing. One way to test whether infinity is real would be to observe something that never stops increasing. So far, no physical system has shown true infinity. Every known structure, from atoms to galaxies, has limits. Even the fastest growing things in nature, like populations of bacteria, eventually slow down due to resources running out. This suggests that infinity, while useful in equations, might not be part of physical reality. But what if infinity does exist? If time stretches forever, does that mean the past is infinite too? Many scientists believe the universe had a beginning, known as the Big Bang. If that is true, then time is not infinite in the past. But if the universe is cyclic, constantly expanding and contracting, then time might have no true beginning or end. This remains an open question in physics. Another challenge is whether humans can truly understand infinity. Our brains evolved to deal with finite experiences: food, shelter, seasons. We can grasp large numbers, but infinity is different. Some people argue that infinity is only a mental construct, a way for the human mind to handle the unknown. Others say that because mathematics describes the universe so well, infinity must be more than just an idea. Different cultures and philosophies have wrestled with infinity in various ways. In some religious traditions, infinity represents the divine or the eternal. In Buddhism, for example, the endless cycle of birth and rebirth reflects an infinite process. In Christianity and Islam, God is often described as infinite. These interpretations show how infinity can take on symbolic meanings beyond numbers and science. So, is infinity real? If real means something physical, then no one has found direct evidence of an infinite thing. If real means useful, then infinity is clearly a part of how we understand the world. Mathematics depends on it, physics grapples with it, and philosophy debates it. The fact that infinity appears in so many fields suggests that, at the very least, it is a fundamental part of how humans describe reality. But whether it exists in nature or only in thought remains an open question. What makes infinity fascinating is that it challenges the limits of human knowledge. It appears to exist everywhere and nowhere at the same time. The universe might be infinite, but we cannot see the whole thing. Time might go on forever, but we only live for a brief moment. Infinity could be a deep truth of reality, or it might be a trick of the mind. Either way, it remains one of the most intriguing mysteries of existence. We move through the world in 3 dimensions: up and down, left and right, forward and backward. These directions make up the space we live in, and everything we see follows these rules. But some scientists believe there might be more to reality than the space we experience. Hidden dimensions, if they exist, could explain mysteries in physics, from gravity's strange weakness to the fundamental nature of the universe. The idea of extra dimensions is not new. More than a century ago, mathematicians explored spaces with 4, 5, or even infinite dimensions. In everyday life, we don't experience them, so they remained an abstract idea. But in the 20th century, physicists began to take them seriously. One reason was Einstein's theory of relativity. He showed that time is not separate from space, but part of a four-dimensional system called spacetime. That was a leap in understanding, but it still didn't suggest extra-physical dimensions. Those ideas came later from quantum mechanics and theories of fundamental forces. Gravity is the first clue that more dimensions might exist. Compared to other forces, like electromagnetism, gravity is weak. A small magnet can lift a paperclip off a table, overcoming the pull of the entire Earth. That seems odd. Some physicists propose that gravity spreads into extra dimensions, making it weaker in our familiar three-dimensional space. This could explain why it is so much less powerful than the other forces. String theory, a leading candidate for a theory of everything, predicts extra dimensions. It suggests that the smallest building blocks of the universe are not tiny particles, but vibrating strings of energy. The way these strings vibrate determines what kind of particle they become. For string theory to work mathematically, the universe must have more than 3 dimensions. Most versions suggest there are at least 10, with 7 of them hidden from view. These extra dimensions could be curled up into tiny shapes too small for us to notice. To picture this, imagine an ant walking on a garden hose. From far away, the hose looks like a simple line. But if you zoom in, you see that the ant can move not only forward and backward, but also around the hose's surface. The extra movement around the hose represents how a dimension can be hidden from a larger perspective. If our universe has extra dimensions, they might be curled up in a similar way, only on a scale much smaller than anything we can detect. Scientists have looked for evidence of hidden dimensions in many ways. One method involves particle physics experiments. When particles collide at high speeds, they release energy. If extra dimensions exist, some of that energy could leak into them, making it seem like energy disappears. The Large Hadron Collider, the world's most powerful particle accelerator, has searched for signs of this happening. So far, it hasn't found any, but the search continues. Another way to test for extra dimensions is through gravity. If gravity spreads into other dimensions, it might behave differently at very small distances. Scientists have tested this by measuring gravity at the smallest scales possible, using precise instruments. They are looking for deviations from what is expected in 3 dimensions, but so far, no clear evidence has appeared. Despite the lack of direct proof, the idea of hidden dimensions remains appealing because it could solve deep problems in physics. It might unify all the fundamental forces, explaining why the universe follows certain mathematical patterns. It could also suggest that our perception of space is limited. Just as people once believed the Earth was flat, we might one day discover that our reality is shaped by unseen dimensions beyond our everyday experience. Some theories go even further, suggesting that entire worlds could exist in these hidden dimensions. If they are large enough, they might hold their own galaxies, stars, and even life. These worlds would be completely separate from ours, invisible and unreachable except through gravity or exotic physics experiments. This idea, known as the brain world scenario, comes from string theory and proposes that our universe exists on a 3-dimensional surface inside a higher dimensional space. If hidden dimensions exist, they might also explain strange cosmic phenomena. Dark matter is one mystery that extra dimensions could help solve. Scientists know dark matter exists because of the way galaxies behave, but they don't know what it is. Some ideas suggest that dark matter could be regular matter trapped in an unseen dimension, exerting gravity but otherwise invisible to us. This would explain why dark matter doesn't interact with light or ordinary matter in a way we can detect. Science fiction often explores the idea of extra dimensions, imagining parallel universes or hidden realities just beyond our reach. While these stories are creative, the real science behind extra dimensions is more subtle. If they exist, they are not places we can visit by stepping through a portal. They would be part of the structure of reality itself, shaping the universe in ways we don't yet fully understand. One challenge in proving hidden dimensions is that our tools are limited. We can only observe the universe with the technology we have, and much of physics depends on what we can measure. If extra dimensions are extremely small, detecting them might require energy levels far beyond what we can achieve with current experiments. Some scientists believe future particle accelerators or advanced gravitational measurements might finally reveal their presence. Even if we never find hidden dimensions, the search itself is valuable. It pushes the boundaries of what we know and forces us to ask deeper questions about the nature of reality. Physics has a long history of overturning assumptions. People once believed space was an empty void, but now we know it is filled with fields and particles. They thought time was separate from space, but Einstein showed they are linked. Discovering extra dimensions would be another revolution, changing our understanding of the universe in profound ways. For now, the mystery remains. If extra dimensions exist, they hold secrets that could reshape physics, explaining puzzles that have troubled scientists for decades. If they do not exist, their absence will also teach us something fundamental about reality. Either way, the search continues, driven by curiosity and the desire to understand the true nature of the universe. The answers may be hidden, but history has shown that persistence in science often leads to unexpected discoveries. The universe appears orderly. We see patterns in nature, from the orbits of planets to the veins in leaves. Scientists describe these patterns with math. Equations explain motion, gravity, and energy. The question is why? Why does the universe follow rules? Why isn't it random? Imagine tossing a handful of sand into the air. The grains scatter, but they don't fly off in any direction they please. Gravity pulls them down. Air resistance slows them. The laws of physics govern every grain. The same happens on a larger scale. Planets follow set paths around stars. Galaxies form in spirals. Atoms arrange in predictable ways. Nothing moves without a reason. This order suggests a deeper structure. If reality were random, we might expect objects to appear and vanish. Motion might be unpredictable, yet we can predict eclipses years in advance. We can calculate how much fuel a rocket needs to reach Mars. This level of precision shows that reality runs on rules, but it doesn't explain why those rules exist. Mathematics gives us tools to describe nature. The equation F equals ma tells us how force, mass, and acceleration relate. Einstein's E equals mc squared links energy and mass. These formulas aren't just useful, they seem built into reality itself. A falling apple and a black hole follow the same laws. A snowflake and a galaxy both form in fractal-like shapes. The same mathematical ideas appear in different places. The question remains, why does nature follow mathematical patterns at all? Some argue that math is a human invention. We created numbers to count things. We wrote equations to model what we see. In this view, the universe isn't inherently mathematical. We just use math to describe it. But this view has problems. Math predicts things before we observe them. Scientists used equations to predict black holes before finding them. The periodic table predicted new elements before they were discovered. If math were just a tool, it wouldn't reveal hidden truths. Instead, it seems to be part of reality itself. Another idea is that the universe must be ordered for us to exist. This is called the anthropic principle. If physics were chaotic, planets wouldn't form, life wouldn't develop, we wouldn't be here to ask the question. This explanation shifts the focus. It doesn't tell us why the universe is orderly. It only says that if it weren't, we wouldn't notice. But that doesn't satisfy everyone. The deeper question remains, why does an ordered universe exist at all? Some scientists think order comes from simplicity. The laws of physics arise from basic principles. Consider a soap bubble. It always forms a sphere, not because it chooses to, but because a sphere minimizes energy. In the same way, reality might follow simple rules that lead to complex patterns. But where do those simple rules come from, and why do they work so well? Another perspective comes from information theory. Some researchers suggest the universe runs like a computer program. Reality follows a code. The laws of physics are its instructions. This idea isn't as strange as it sounds. Computer simulations use math to create digital worlds. If the universe behaves like a program, its order comes from its underlying code. But that leads to another question: who or what wrote the code? Philosophers have wrestled with this problem for centuries. Plato believed mathematical forms were the true reality. He thought the physical world was a shadow of a deeper, abstract order. Others suggest the universe follows rules because it must. If reality were chaotic, it wouldn't exist in any stable form. But why should stability exist in the first place? Some theories push the question further. Maybe there are countless universes, each with different laws. In most, chaos reigns. In a few, order emerges. We happen to live in one of the ordered ones. This idea, called the multiverse theory, suggests that order isn't special. It's just one possibility among many. But we have no proof of other universes. And even if we did, we'd still need to explain why any of them have order at all. Physics has limits. Some things remain unknown. We don't fully understand why particles have the properties they do. We don't know why the speed of light is constant. We have equations that describe these things, but we don't know why they are true. This gap in understanding fuels both scientific and philosophical debates. Despite these mysteries, one thing is clear: order exists. The sun rises and sets predictably. Water freezes at a set temperature. DNA replicates with astonishing precision. The rules governing these processes seem universal. They hold true everywhere we look. If they changed, even slightly, the universe might collapse. Stars might not form. Atoms might not hold together. The fact that these laws work together so perfectly is astonishing. Could the universe have been different? That's another puzzle. If we change the laws of physics, would a new order emerge, or would everything fall apart? Some believe only certain kinds of laws allow stable structures. If that's true, then our universe follows the only rules that work. But why should any rules work at all? Some look for answers in deeper physics. Maybe a more fundamental theory explains why reality has rules. Physicists search for a theory of everything, a single framework that unites all known forces. If they find it, it might reveal why order exists. But even then, a final question lingers. Why does that theory exist? Why does anything follow rules instead of chaos? The mystery remains. We can describe the universe's order, we can use it to make predictions, we can even question where it comes from, but we don't yet have an answer. The search continues. Computers have changed how we live. They calculate, predict, and automate. They help us solve problems that once seemed impossible. But there are limits to what a computer can do. Some problems will never be solved by any machine, no matter how powerful it becomes. This is not because of hardware limits or bad programming. It is a fundamental truth about the nature of computation. To understand this, imagine you have a powerful supercomputer. You give it a math problem. It solves it in seconds. You give it a harder one. It takes a bit longer, but still gets the answer. Now you give it something much harder, so difficult that no computer today could solve it in a lifetime. But you trust that, given enough time, the answer will come. The question is, are there problems that no computer can ever solve, no matter how much time you give it? The answer is yes. One example comes from an old question in logic and mathematics. In the 1930s, Alan Turing, the father of modern computing, discovered something surprising. He proved that some problems are undecidable. That means there is no step-by-step method or algorithm that can always solve them. The most famous is the halting problem. Imagine you have a program that takes an input and runs. You don't know if it will stop or keep going forever. You want another program to analyze it and tell you with certainty whether it will ever stop. Turing showed that no such program can exist. If it did, it would create a paradox that breaks logic itself. This discovery changed everything. It meant that some problems are beyond the reach of computation. No matter how fast a computer is, no matter how much memory it has, it will never be able to solve these problems. They are not just difficult, they are impossible. Another example comes from the world of numbers. There are equations so complex that no formula exists to solve them. Some equations have solutions that can be found with effort. Others have no solutions at all, and we can prove this. But there's a third category. Equations where we don't know if a solution exists and no computer can tell us for sure. These equations sit at the edge of what is knowable. Mathematicians can look for patterns and try different methods, but some will remain unsolved forever. There are also problems where the answer exists, but no computer can reach it in a reasonable time. These are called intractable problems. They don't break logic, like the halting problem, but they take too long to solve. Imagine a safe with a long password. A simple computer might take thousands of years to guess it. A better computer might do it in days. But some problems get so complex that even the best computers would need more time than the age of the universe. These problems are solvable in theory, but in practice, they might as well be impossible. One famous example is the traveling salesman problem. A salesman wants to visit a list of cities and take the shortest route. If he has only a few cities to visit, a computer can find the best path quickly. But as the number of cities grows, the number of possible routes explodes. Soon, even the most powerful computers struggle. The best they can do is guess a good route, but they will never be sure it is the shortest one. This problem appears in many real-world situations, from delivery routes to DNA sequencing. Scientists look for clever shortcuts, but the fundamental difficulty remains. Another limit of computation comes from physics itself. Computers are made of physical parts. They follow the laws of nature. If a problem requires more energy or space than the universe allows, it can never be solved. Imagine a computer so large it needs more atoms than exist in the universe. That computer is impossible to build. Some problems may require calculations that need more energy than all the stars combined can produce. These limits are not just technical, they are physical. Some people believe that quantum computers might change things. These machines use the strange rules of quantum mechanics to process information in new ways. They are not just faster, they are fundamentally different from normal computers. For some problems, they could be a game changer, but they won't break the limits of computation. Even a perfect quantum computer would still be bound by the same rules of logic and physics. It might solve some problems that are too hard for regular computers, but it won't solve the truly impossible ones. The idea that some things can never be known is unsettling. We like to believe that given enough time, we can solve anything. But the universe does not work that way. Some questions will never have answers. Some patterns will never be discovered. Some problems will always remain beyond our reach. Despite these limits, computation has opened new doors. Even when we cannot solve a problem perfectly, we often find ways to get useful answers. Weather forecasts are never exact, but they are good enough to guide decisions. Medical research cannot predict every outcome, but it can save lives. Engineers cannot design perfect systems, but they can make them work well enough. Understanding the limits of computation helps us focus on what matters. If a problem is impossible, we can stop wasting time on it. If it is merely difficult, we can look for better methods. If it is unsolvable in a lifetime, we can find ways to approximate the answer. Knowing our limits does not mean giving up. It means working smarter. There will always be mysteries beyond computation, but that does not mean we stop asking questions. Some of the greatest discoveries in history came from people searching for the impossible and finding something unexpected along the way. The limits of computation do not limit our curiosity. They give us a clearer view of what is possible and what lies forever beyond our grasp. The idea of parallel universes suggests that there are other versions of reality, possibly infinite in number, where different events have played out. If true, this means that somewhere, another version of you made a different choice this morning, took a different job, or never existed at all. It's a strange thought, but some serious scientific theories suggest that parallel universes could be real. One way to think about parallel universes is through quantum mechanics. This branch of physics describes how particles behave at a microscopic level. According to the many worlds interpretation, every time a decision is made, the universe splits. If you decide to wear a blue shirt instead of a red one, the universe doesn't pick just one outcome. Instead, it splits into two, one where you wore blue and another where you wore red. These separate realities continue, each evolving on its own path. This means that every possible outcome of every event could exist in a different universe. This idea helps explain why quantum particles seem to exist in multiple states at once until observed. If reality splits, then each possible state continues in its own branch. Another way to think about parallel universes comes from cosmology, the study of the universe as a whole. The observable universe is just a portion of a much larger space. Light from distant galaxies has only had a limited time to reach us, so we can only see so far. Beyond what we can see, space might continue forever. If it does, then there's a good chance that some regions of space look identical to ours. With infinite space, the number of possible ways particles can arrange themselves is also infinite. This suggests that somewhere far beyond our reach, there could be a version of Earth with people who look and act just like us. Some scientists believe in the concept of a multiverse, a collection of many universes. Different theories suggest different ways these universes could exist. One possibility is that each universe is like a bubble in a vast cosmic foam. These bubbles might form when space expands rapidly in a process called inflation. If true, our universe is just one bubble among countless others. Some might have different physical laws, where gravity is weaker or atoms don't form the same way. In some, life might not be possible. In others, intelligent beings might exist in ways we can't imagine. Despite these ideas, we don't have direct evidence of parallel universes. The challenge is that if they exist, they might be completely separate from our own. We can't travel to them or communicate with them. If another version of you exists, you will never meet them. Some physicists argue that without a way to test the existence of these other worlds, the idea is just speculation. Others believe that indirect evidence could come from unusual patterns in cosmic radiation, the afterglow of the Big Bang. Some think that if another universe collided with ours in the past, it might have left a trace. So far, no such evidence has been found. Philosophers and scientists debate whether parallel universes would change how we think about choice and responsibility. If every possible version of you exists somewhere, does that mean free will is an illusion? If one version of you made a mistake, but another avoided it, does it matter what you do? Some argue that since we only experience one version of events, the existence of others is irrelevant to our decisions. Others say that knowing every possibility plays out somewhere takes away the uniqueness of our choices. Stories and movies have played with the idea of parallel universes for years. Some tell stories where characters travel between worlds, meeting different versions of themselves. In reality, if parallel universes exist, they are likely unreachable. They may exist as separate branches that never connect. If they are far away in space, the distance would be too great to cross. Even if they exist, we may never know for sure. Some people wonder if the Mandela effect, where large groups of people remember events differently than recorded history, could be evidence of shifting between realities. Others believe that strange coincidences might hint at unseen connections between worlds. Most scientists, however, say these are just tricks of memory and perception. Even though we don't have proof, the idea of parallel universes helps scientists think about big questions. Why does our universe have the laws it does? Are there other places where conditions are different? If we ever find evidence, it would change our understanding of reality in a profound way. Until then, parallel universes remain one of the greatest mysteries of science. People have long wondered if we are alone in the universe. With billions of stars in our galaxy and billions of galaxies beyond, it seems likely that life exists elsewhere. If that's true, why haven't we seen any clear evidence of alien civilizations? This question, known as the Fermi paradox, remains one of the biggest mysteries in science. The problem begins with the numbers. The Milky Way alone has around 100 billion stars. Many of these stars have planets, and a good number of those planets fall into the habitable zone, where conditions could support life. Given enough time, some of those planets should develop intelligent life. If even a small fraction of them did, the universe should be teeming with civilizations. Some of those civilizations should be millions of years ahead of us, technologically speaking. That means they should have colonized the galaxy, or at least sent signals into space that we could detect. Yet, we see nothing. One possible explanation is that intelligent life is much rarer than we think. Maybe life itself is common, but intelligence is not. Bacteria and simple organisms might thrive on many planets, but developing into something as complex as humans might be incredibly difficult. If we look at Earth's history, life appeared fairly early, but it took billions of years to evolve beyond single-celled organisms. Intelligence, as we define it, has only existed for a tiny fraction of that time. The leap from simple life to intelligent beings who build technology may require a chain of events so unlikely that it has only happened once, here. Another possibility is that intelligent civilizations exist, but destroy themselves before they can spread into space. This is known as the Great Filter Theory. The idea is that there is some barrier that most life cannot pass. It could be that natural disasters, wars, or resource depletion wipe out civilizations before they get the chance to expand beyond their home planets. If that's true, the silence we hear from space might be because intelligent life keeps wiping itself out. Some scientists think we might not be looking in the right way. Most of our search for alien life involves listening for radio signals. But what if advanced civilizations don't use radio waves? We moved from sending radio signals to fiber optic cables in just a few decades. A civilization thousands or millions of years ahead of us might use technology we can't even imagine. If that's the case, they could be broadcasting signals that we have no way to detect. Then there's the idea that advanced civilizations might not want to communicate. If they exist, they could be deliberately staying quiet. They might see us the way we see ants, too primitive to bother with. Or they could worry that making themselves known would invite danger. Some scientists, like Stephen Hawking, warned that reaching out to alien civilizations might not be wise. If there are aggressive species out there, advertising our existence could put us at risk. This concept, known as the dark forest theory, suggests that intelligent life might avoid contact to stay safe. Another possibility is that civilizations are out there, but they exist in a way we don't understand. Maybe they live on planets where we aren't looking, such as moons around gas giants or underground oceans beneath thick ice. Maybe they exist in digital form, having uploaded their consciousness into vast computer networks. Or perhaps they don't live in the physical world at all, but instead exist in ways beyond our comprehension. If life can evolve in radically different ways than we expect, we might not recognize it, even if it's right in front of us. It's also possible that we have already seen evidence of aliens, but didn't recognize it. Some scientists have suggested that mysterious objects like Oumuamua, an interstellar object that passed through our solar system in 2017, could be artificial. Others wonder if strange signals we have picked up, like the famous WOW signal from 1977, might be attempts at communication. So far, no conclusive proof has been found, but that doesn't mean we aren't overlooking something. Some people believe that aliens have already visited Earth, but that governments or other forces are keeping it a secret. UFO sightings and reports of alien encounters have been around for decades, if not centuries. While most of these reports can be explained as natural or human-made phenomena, a small number remain unexplained. Even with official reports from military pilots who have seen objects that defy known physics, there is no solid proof that these objects come from extraterrestrial civilizations. One last possibility is that we are the first. If intelligent life is rare and civilizations tend to destroy themselves, it could be that we are among the first species to develop the ability to explore the stars. If that's true, the future of intelligent life in the universe depends on what we do next. For now, we keep listening, searching, and wondering. The universe is vast, and our understanding is still young. If there are other civilizations out there, time may reveal them. Until then, we remain alone, at least as far as we know. Many people claim to have seen ghosts. Some say they've heard voices in empty rooms or felt a sudden chill for no reason. Others report seeing figures that vanish or objects moving on their own. Stories about ghosts appear in every culture, passed down through generations. But do ghosts really exist, or is there another explanation? To answer that, we need to look at the evidence. Scientists study the world by testing ideas and looking for patterns. When it comes to ghosts, the evidence is mostly stories and personal experiences. These stories are powerful, but they don't always prove that ghosts are real. The mind can play tricks, and people often see what they expect to see. Imagine walking through an old house at night. The floor creaks under your feet. The wind makes a soft whistle through a crack in the window. You feel like someone is watching you. Your heart beats faster. Then you hear a faint whisper. Is it a ghost, or is your mind filling in the blanks? Psychologists say that the human brain is wired to recognize patterns, even when they aren't there. This is called pareidolia. It's why people see faces in clouds or hear voices in static noise. When someone believes in ghosts, They might interpret normal sounds or shadows as something supernatural. Another explanation is sleep paralysis. Some people wake up and find that they can't move. They feel pressure on their chest as if something is sitting on them. Many describe seeing a dark figure in the room. It feels terrifying, but scientists say it happens when the brain is caught between sleep and wakefulness. The body is still in sleep mode, but the mind is awake, creating a dreamlike hallucination. There's also the power of suggestion. If someone tells you a house is haunted, you might feel uneasy when you enter. You might hear a strange noise and assume it's a ghost. But if no one had told you the house was haunted, you might not have noticed the noise at all. Ghost hunting shows and horror movies add to this effect, making people more likely to believe in ghosts. Some ghost sightings may have a physical explanation. Old buildings often creak and groan as they settle. Pipes make knocking sounds. Drafts can move curtains. Certain frequencies of sound, called infrasound, can make people feel anxious or even see things that aren't there. Some scientists believe that exposure to low-frequency vibrations can cause ghostly experiences. Another theory involves carbon monoxide poisoning. In the past, people reported seeing ghosts in old houses with gas lighting. Later, researchers found that these houses often had leaks. Breathing in carbon monoxide can cause hallucinations, dizziness, and a feeling of dread. In some cases, people who thought they saw ghosts were actually suffering from carbon monoxide exposure. Even with these explanations, some experiences remain puzzling. There are reports of people seeing the same ghost in the same place years apart. Sometimes, a person claims to see a ghost with details they couldn't have known about beforehand. These cases are harder to dismiss, but they don't necessarily prove that ghosts exist. Memory is unreliable. People remember things differently over time, and details can change. A person who hears a ghost story might later believe they saw the ghost themselves. Some researchers study the idea that ghosts could be a form of energy. The law of conservation of energy says that energy can't be created or destroyed, only changed. When a person dies, what happens to their energy? Some believe it lingers as a ghost. But scientists say there's no proof that energy can take the form of a spirit. When a body stops functioning, its energy disperses into the environment as heat. There's also the question of why ghosts would behave the way people describe them. If ghosts are spirits of the dead, why do they only appear in certain places? Why do they wear clothes? If a ghost is the soul of a person, why would objects like a chair or a ship also be haunted? These questions suggest that ghosts, as commonly described, don't fit with how the physical world works. Still, belief in ghosts remains strong. Some people say they've seen too much to dismiss. Police officers, doctors, and soldiers have all shared experiences they can't explain. Even skeptics sometimes have encounters that leave them questioning. The human experience is full of mysteries, and not everything has a clear answer. Ghost stories will likely continue as long as people keep experiencing strange things. Whether ghosts exist or not, the idea of them serves a purpose. Ghost stories give people a way to talk about death, loss, and the unknown. They provide comfort to those who have lost loved ones and entertainment to those who enjoy a good scare. Science may never prove that ghosts exist, but it may also never prove that they don't. Until then, the mystery remains. People have been trying to talk to the dead for thousands of years. Across cultures and time, there are stories of ghosts, spirits, and voices from beyond. Some believe they have spoken to lost loved ones, while others dismiss these experiences as tricks of the mind. But can we truly communicate with the dead? If consciousness continues after death, it would change everything we know about life and existence. If it does not, then every attempt at contact is simply a reflection of our own thoughts and emotions. Many who claim to have contacted the dead describe their experiences as deeply personal. A widow hears her husband's voice in the middle of the night. A mother feels her child's presence long after they've passed. Sometimes, people report vivid dreams where the deceased seem to speak clearly. These moments feel real to those who experience them. The emotions are powerful, but are they real in a physical sense, or do they come from within the mind? Science has no solid proof that the dead can speak to the living. Most studies suggest that experiences of ghosts or spirits come from the brain. When we lose someone, our minds struggle to accept it. The brain is powerful, capable of recreating voices, smells, and even visions of those we've lost. This is known as grief hallucination, and it is surprisingly common. A person grieving might hear a familiar laugh or see someone in a crowd who looks exactly like their loved one. The mind, in its longing, fills in the gaps. Some believe that modern technology might offer a way to bridge the gap between life and death. There are devices, such as spirit boxes, that scan radio frequencies quickly, creating bursts of noise. People using these devices claim to hear voices in the static. Skeptics argue that the human brain is wired to find patterns, even when none exist. A random burst of sound might resemble a word, and once a person expects to hear a voice, they are more likely to perceive one. There are also mediums, people who claim to have a special ability to talk to spirits. Some mediums conduct seances, where a group gathers in a dimly lit room, hoping to hear from the beyond. Others perform readings, speaking to individuals about their lost loved ones. Sometimes they reveal specific details that seem impossible to guess. But many so-called psychics use cold reading, a technique where vague statements are made until the person seeking answers fills in the blanks. When a medium says, "I feel a father figure here," the person might respond, "My dad died last year," giving the medium more information to work with. Despite skepticism, there are cases that defy easy explanation. Some people report messages from the dead in ways that seem impossible to fake. A woman might find a letter from her grandmother at the exact moment she needed guidance. A child might describe a past life with details they could not have known. These stories are rare, but they make some question whether there is more to reality than what science can measure. One of the strongest arguments against communication with the dead is the lack of clear, repeatable evidence. If spirits could talk, why wouldn't they provide undeniable proof? Why do messages always come in vague signs, flickering lights, or random words on a ghost hunting device? If a spirit wanted to send a message, why wouldn't it simply write it down or appear in a clear form? Some argue that spirits exist in a different plane of existence, making communication difficult. Others believe that most experiences of ghosts or voices are just products of the mind. There is also the question of what consciousness really is. Neuroscience suggests that thoughts, memories, and emotions come from the brain. If the brain stops working, does that mean the mind stops too? Or does consciousness exist separately, able to continue after the body dies? Some believe in a soul, something that lives on beyond death. If that is true, then communication might be possible. But if consciousness is just a function of the brain, then when the brain stops, so does the mind. Some experiments have tried to test whether people can send messages after death. One famous example involved a locked box. A scientist wrote a secret message and sealed it inside. He claimed that if he could communicate after death, he would reveal the message to a medium. Years passed, and many tried, but no one was able to guess what was inside. It remains locked, untouched, a quiet statement that if an afterlife exists, it does not make communication easy. Despite the lack of evidence, the idea of speaking to the dead remains powerful. It offers comfort. If the dead can hear us, then they are not truly gone. If they can answer, then death is not an end, but a transition. It is no surprise that many want to believe. Losing someone is one of the hardest things a person can go through. The thought that they might still be near, watching, listening, perhaps even sending signs, is a source of peace. In the end, whether or not the dead can communicate with the living is a question without a clear answer. Science leans toward no, pointing to psychology, brain function, and the power of suggestion. But experience tells another story, one filled with whispers in the dark, dreams that feel more than dreams, and moments where the presence of the dead feels undeniable. The question remains open. Either we have not yet found the right way to listen, or the voices we hear are echoes of our own longing. Reality feels solid. The ground holds steady beneath our feet. The sun rises and sets on schedule. We live, we think, we act. But what if none of it is what it seems? What if everything we perceive is part of a shared dream, a collective experience rather than an independent physical world? A dream feels real while you're in it. You see people, places, and events unfold in ways that make sense at the time. You believe you're there, experiencing everything firsthand. But when you wake up, the world of the dream disappears. You realize it was all in your mind. What if waking life isn't so different? What if our entire experience of reality is a kind of dream, not just in one person's mind, but shared across many minds at once? Most people assume the physical world exists independently of them. We touch objects and they push back. We talk to people and they respond. This gives the impression of a stable, external reality. But we never directly experience the world itself. Instead, we experience our perception of it. Our eyes take in light, but it's our brain that turns that light into images. Our ears pick up vibrations, but it's our brain that turns them into sound. Every sensation we have is processed internally. That means everything we think is out there is actually happening inside our heads. Consider a dream. When you dream, you see, hear, and feel things just like you do when you're awake. You accept them as real until you wake up. But in a dream, there is no external world causing those sensations. They are generated from within. What if waking life works the same way? What if the only reason it feels real is that we all experience it together? A philosopher named George Berkeley suggested something similar in the 18th century. He argued that objects don't exist independently of perception. If no one is looking at a tree, the tree does not exist. It only comes into being when observed. He believed everything exists in the mind of God, which keeps the world consistent even when no one is watching. This idea may sound strange, but modern science hints at something similar. Quantum physics suggests that observation plays a role in how reality behaves. When a scientist looks at a particle, it acts like a particle. But when it is not being observed, it behaves like a wave, existing in many places at once. This suggests that observation might create reality rather than simply record it. If true, this raises the question, who or what is doing the observing? If reality is a collective dream, then it isn't built from matter. Instead, it is made from shared consciousness. That would explain why different people can agree on what they see and hear. If you and a friend walk into a room, you both see the same furniture. But that doesn't prove the furniture exists independently. It only proves that you both perceive it the same way. In a shared dream, people can experience the same dream world while still being asleep in different places. This idea also appears in some ancient traditions. Hinduism describes reality as Maya, an illusion created by collective consciousness. Buddhism teaches that attachment to the physical world comes from a misunderstanding of its true nature. Mystical experiences often involve a sense of unity, as if the boundary between self and world disappears. People who have near-death experiences sometimes report that reality felt more like a thought than a solid place. Could these experiences reveal something fundamental? If reality is a dream, who is dreaming it? One possibility is that each person contributes to the dream. If so, then our thoughts and beliefs shape the world more than we realize. Another possibility is that a single consciousness generates reality, and we are all parts of it. This would mean our individual identities are illusions, just as characters in a dream seem separate but all come from the same mind. This idea has implications. If reality is a dream, death might not be the end. When you wake from a dream, the dream disappears, but you continue. If waking life is another kind of dream, then perhaps we continue in some form after death. It might mean the boundaries between people are not as solid as they seem. If everything is part of one shared consciousness, then harming another person is like harming yourself. Skeptics argue that this view is unnecessary. They say the physical world exists regardless of whether we perceive it. But they face a problem. No one has ever directly experienced anything outside of consciousness. Every test, every experiment, every observation happens within a mind. If something exists outside of consciousness, we have no way to prove it. That doesn't mean the physical world isn't real, but it does mean we can't be certain it is. Science assumes an external reality because it works well for making predictions, but practical usefulness doesn't guarantee truth. Many assumptions work well, but later turn out to be wrong. People once assumed the Earth was flat because it felt that way. Later, they assumed space was filled with an invisible ether that carried light. That idea was useful for a time, but was eventually discarded. The idea of an external world might be another assumption waiting to be challenged. Imagine waking up in a different reality, one where you remember this world as a dream. How would you know that new reality is the true one? What if there is no final, absolute reality, only layers of dreams, each one feeling more real than the last? Some people who experience lucid dreams describe waking up into yet another dream, believing they are awake, only to wake up again. This suggests that reality might not have a single ultimate level. If reality is a collective dream, does that change how we should live? It might mean we have more control than we think. In a lucid dream, people can change their surroundings by willpower alone. If waking life is also a dream, perhaps our beliefs and intentions shape our world more than we realize. That would mean fear and doubt keep us trapped, while awareness and understanding open new possibilities. This idea is unsettling for some. It challenges deep assumptions, but it also offers hope. If reality is a dream, then suffering might not be absolute. Just as nightmares end when we wake up, perhaps pain and struggle are temporary states. If we are all part of a shared consciousness, then we are not alone. We are connected in ways we do not yet understand. No one can prove whether reality is a dream, but we can question our assumptions. We can ask what it means to experience anything at all. We can explore the nature of consciousness, not through theory alone, but through direct experience. If reality is a collective dream, then understanding it might be less about science and more about waking up. When we look at the world, we assume we see it as it is. A tree appears green, the sky looks blue, and objects feel solid. But what if this experience is not reality itself, but just a version shaped by our senses? Everything we know comes through sight, sound, touch, taste, and smell. These senses help us navigate life, but they also have limits. Consider color. The green of a leaf is not an inherent property of the leaf. It reflects certain wavelengths of light, and our brains interpret that light as green. Other creatures see it differently. A dog, for example, sees fewer colors than a human. A mantis shrimp, with its 16 types of color receptors compared to our 3, sees a world we cannot imagine. The leaf remains the same, but its color depends on the observer. If color is not an objective trait, then how much of our experience is just a mental interpretation? Sound works the same way. A tree falling in the forest creates vibrations in the air. If no one is there to hear it, does it make a sound? The vibrations exist, but sound itself only happens when an ear picks up those vibrations and the brain processes them. To a deaf person, the event is silent. That means sound is not a feature of the world, but something created in the mind. Touch is also deceptive. We think we feel objects directly, but that is not true. When you press your fingers against a table, the sensation of hardness is not from direct contact. At the atomic level, there is space between the electrons of your skin and the table's surface. Electromagnetic forces repel each other, preventing true physical contact. What you feel is the force, not the object itself. Even time may not be as it seems. We experience it as a steady flow, moving from past to present to future. But physics suggests time is not fixed. Einstein's theory of relativity shows that time moves at different speeds depending on gravity and velocity. An astronaut moving at near light speed would experience time more slowly than someone on Earth. If time is flexible and not universal, then our everyday sense of it may be an illusion. Our perception of reality depends on the brain's ability to process information. The brain receives signals from the senses and turns them into a meaningful picture, but it does not capture everything. Our eyes only detect a narrow range of the electromagnetic spectrum. We cannot see infrared, ultraviolet, or X-rays, but many animals can. A snake sees infrared heat signatures of its prey. A bee sees ultraviolet patterns on flowers that guide it to nectar. These creatures experience a world we cannot access. Our brains also fill in gaps and make assumptions. Optical illusions reveal how easily the mind can be tricked. The Miller-Lyer illusion, where two lines of equal length appear different because of arrow-like markings at their ends, shows how our brains misinterpret visual cues. This is not a failure, but a feature. The brain takes shortcuts to process information quickly. In most cases, these shortcuts help us make sense of the world. But they also show that what we see is not always what is there. Memory works the same way. We think of memories as recordings of the past, but they are reconstructions. Each time we recall an event, the brain fills in details, sometimes incorrectly. Over time, memories change. This means even our sense of personal history is not entirely reliable. If our memories, vision, and hearing do not provide an exact picture of reality, what does? Some scientists and philosophers suggest that we do not perceive reality directly, but only an interface. Like a computer screen hides complex circuits behind simple icons, our senses may present a simplified version of reality that helps us survive. This idea, called the interface theory of perception, suggests that evolution favors useful perceptions over true ones. Seeing a ripe fruit as red helps us find food, regardless of what the fruit is at a molecular level. Seeing depth helps us avoid cliffs, whether or not depth exists as we perceive it. Consider virtual reality. When wearing a VR headset, a person can feel present in a digital world. They see objects, hear sounds, and move through space, even though nothing is physically there. The brain accepts the illusion. If our senses can be fooled so easily, how do we know our everyday experience is not another kind of constructed reality? Some experiments suggest this may be true. Studies in neuroscience show that the brain can generate experiences without external input. In sensory deprivation tanks, where all external stimuli are removed, people begin to see colors, hear sounds, and even feel touch sensations that are not real. The brain creates reality even when nothing is there to perceive. This raises deeper questions. If our perception is just an interpretation, is there an objective reality at all? Some physicists argue that at the quantum level, reality does not exist in a fixed state until it is observed. The famous double-slit experiment shows that particles behave differently when measured, as if observation itself changes reality. If this is true, then our role as observers may shape what we consider real. Some thinkers take this further, suggesting reality might be more like a shared dream or a simulation. If all we know comes from sensory inputs processed by the brain, then in theory, an advanced system could feed us an entirely artificial reality. This idea, popularized in science fiction and philosophy, suggests that we may never know the true nature of existence. Still, for practical purposes, our perception works well enough. We navigate the world, interact with others, and survive. Even if we do not see reality as it truly is, we see enough to function. But knowing our limits can be useful. It reminds us to question assumptions, to stay open to new perspectives, and to recognize that the way things appear is not always the way they are. In the end, whether reality exists beyond our perception or is entirely shaped by it remains one of the biggest mysteries. What we do know is that our experience of the world is not the world itself, but a version of it shaped by the mind. That insight alone changes how we see everything.